punchline in your sleep. You're running for your life. You're a young individual running for your life. You're a kid, and your body has better things to do under those circumstances than deposit calcium in your long bones, grow later if there is a later. Short-term stress response, highly adaptive. Chronic stress response, you impair growth. That's the concept that we'll run through the next 2 lectures. Chronic stress, environmental stressors can disrupt the normal growth process. Now, the point of this lecture is one critical fact, which is environment doesn't begin at birth. Environment begins in fetal life. And thus, the consequences of stress can begin in fetal life also. Now, what's environment like for a fetus? What's stress like for a fetus? Well, what it's about is what mom is experiencing. Because you share something absolutely critical with your mother when you're a fetus. You share her circulatory system. And the hormones in her bloodstream will wind up to some extent in your own circulatory system. The amount of nutrients will become relevant in there. You have all sorts of ways in which maternal experience is translated into fetal experience. Even something as straightforward as extremely loud noises, fetuses can respond to. It turns out amniotic fluid is this great vibratory, resonating environment. What's going on in the outside world can affect a fetus. And what we have is the simple punchline here is, well, you don't want to be a stressed fetus. You don't want to have the same sort of stressors that follow the same logic built around grow tomorrow, grow tomorrow. Now, what this begins to bring in are 2 realms of consequences of fetal stress. The first is what you're like at birth, and in the simplest sort of level, more fetal stress equals a lower body weight at birth. What sort of individual you're like at birth. And the other, a much more subtle point, is fetal experience, fetal stress, influencing what sort of adult body you're going to have responding to adult environments. Now, the second subtle point, the notion of fetal experience translating into how your body works as an adult, brings in all sorts of new concepts, one of which can be summarized with terms that are absolutely metaphors. The fact that a fetus makes decisions about what sort of organism to grow into, that a fetus is programmed by experience, by environment. These are metaphorical terms. Things get set down. Things get regulated in a permanent sort of way during fetal life. What do I mean by this? Let me give a first example, and this is an absolutely extraordinary one. I mean, we are all used to this typical sequence of scientific knowledge. In this realm, you study something in laboratory animals, you see how it works, you understand its world, and then you see if it works in humans. This is a case where it started with humans. And this is a phenomenon known as the Dutch hunger winter. 1944, World War II, Holland is occupied by the Nazis, and for a number of reasons, the uprising of resistance among the Dutch against the Nazis, the decision was made to punish Holland and divert all of the food that winter to Germany. And suddenly, Holland, with its reasonably good westernized diet, plunged into famine. Over the course of that famine, something like 16,000 people starved to death. Absolute disaster. And something very interesting came out of it. Suppose you were a fetus, a second or third trimester fetus during the Dutch hunger winter. What's going on? You are experiencing that starvation insofar as there's less nutrients in mom's bloodstream. You are experiencing this environmental stressor. So it turns out that one of the things that a fetus decides, one of the things in which a fetus is programmed to respond to, one of the things going on there is the fetus in effect is deciding, well, how much food is there out there in that world I'm heading into soon? And be a fetus at that time during starvation, and what your body concludes is there's not a whole lot out there. And thus your body gets programmed to be thrifty. What do we mean by thrifty? Every bit of food that hits your bloodstream, quick, store it away. Translated into a few lectures ago, every bit of nutrients that hit your bloodstream secrete insulin like crazy. Every bit of salt that you have, kidneys really good at retaining it because who knows when the next salt is coming. Be really thrifty at storing stuff. So, Dutch hunger winter ends, and suddenly you're going back to a normal, healthy Dutch diet, and everything else being equal, 50 years later, you are now close to 20 times more likely to have metabolic syndrome. Because your body learned as a fetus to be really efficient, really thrifty, really good at storing away nutrients, and you have programmed your metabolic system to work that way forever after. Mind you, if you were a newborn during the Dutch hunger winter, if you were first trimester fetus, it didn't work that way. You don't see this Dutch hunger phenomenon. It happens second and third trimester is when a fetus is programming its response to nutrients, how tripwire of insulin secretion it has. It's during that time that you are programming your adult metabolism. So there we see a really disturbing, remarkable phenomenon. And this turns out to be one of a number of examples of this, number of examples that have been summed by epidemiologist named David Barker as fetal origins of adult disease, FOAD, this completely new area of research built around the notion that environment doesn't begin at birth, and an awful lot of what's going on in fetal life causes programming of how adult responses are going to be remarkable. And soon people were studying this in laboratory animals, seeing experimental versions of prenatal stress, and you see the exact same thing. You can generate a Dutch hunger winter phenomenon. You can show that prenatal stress, and as an adult, you have a less than optimal stress response. You have elevated levels of glucocorticoids basally when there's no stressor. In the absence of stress, prenatally stressed rats, as adults, secrete more glucocorticoids than they're supposed to. Bad news. Prenatally stressed rats, as adults, take a longer time to recover after the end of a stressor for their glucocorticoid levels to go back to normal. Prenatally stressed rats, as adults, are more vulnerable to metabolic syndrome. All sorts of things, even the domain of behavior, anxiety. There's this chemical your brain makes, which is called an endogenous benzodiazepine. Don't panic. The synthetic, the drug version of it is something like Valium or Librium, anti-anxiety drugs. And just like all the other examples we've heard, the benzodiazepines that your brain makes interact with benzodiazepine receptors to decrease anxiety. A prenatally stressed rat as an adult has fewer of those benzodiazepine receptors in its brain, more of a predisposition then towards anxiety. Even in the realm of learning, prenatal stress and something about those elevated glucocorticoid levels disrupt aspects of brain development, aspects relevant to learning and memory. Prenatally stressed rats, everything else being equal from birth on, have more memory problems, aren't quite as good at learning, at consolidating new things, in part because they have elevated glucocorticoid levels as an adult, beginning to disrupt cognition. Stay tuned, that's going to be an entire lecture, but also because of that prenatal environment disrupting brain development. So look at this. We've got this whole world of prenatal stress, which could influence your levels of stress hormones as an adult, how readily you recover from a stress response, your brain chemistry that deals with anxiety, learning, vulnerability to metabolic disease. Again, that critical punchline, which is environment doesn't begin at birth. So there's an even more interesting ripple to this. And what it winds up doing is having Dutch hunger winter effects that are in fact multi-generational. Here's what I mean. You were a Dutch hunger fetus, Dutch hunger winter fetus, and 30 years later, you are now pregnant. You are having a child. Thanks to that fetal experience, you have a thrifty metabolism. You secrete insulin like crazy, so you're really good at stealing nutrients from your circulation. You retain salt, all that sort of stuff. So you are having a perfectly typical diet during your pregnancy, but as I just said, you are stealing a typically large amount of it from your fetus. You are more efficient at taking nutrients out of the bloodstream, so for that perfectly normal diet, your fetus is getting less nutrients than it should. Certainly not starving, but insofar as you're absorbing more of it than normal, your fetus is getting less of it than normal. In other words, Dutch hunger winter babies, when they become pregnant, generate Dutch hunger winter babies. It's multi-generational. This has now been shown in the Dutch hunger winter humans. Their grandkids show some of these same tendencies. It's been shown in laboratory rats as well. This is multi-generational. Mind you, it's not as big of a phenomenon. It's one where it's a ripple of prenatal effect that with each generation gets smaller and smaller, but nonetheless, this is remarkable. Fetal life can leave an imprint, can leave an echo, can leave scar tissue of disease risk multi-generationally. Now this is real critical in lots of ways because you look at this and you say, wow, this could easily be mistaken for something else. In other words, you take a rat who has been made a Dutch hunger winter rat as a result of fetal malnutrition, and as an adult is much better at storing calories, and as an adult, when she's pregnant, gives birth to babies who are a little bit prone towards this Dutch hunger winter phenomenon. You do a laboratory experiment, which is as soon as the babies are born, you take them away from the mom, and they're raised by a different mother. It's called cross-fostering, a standard technique in these experimental studies, and you see a trait in these babies that were fostered elsewhere, a trait that they don't share with their adoptive mother, a trait that they share with their biological mother. As seen here, this propensity towards metabolic syndrome. And you look at that and you say, well, all they had in common was their shared genes, took them away right at birth. Oh, if they have this same tendency towards this metabolic disease as their biological mom, it must be genetic. Look, it's passed on over time. And what we see here is, again, that truism, which is environment doesn't begin at birth. If you're not careful, some of these prenatal programming effects might be mistaken for, in fact, being genetic. Okay, so now we take this and we transition to the next logical phase, which is moving from all this prenatal stress stuff into postnatal, the sort of stress you experience during childhood. And how does that work? What are the general consequences? You know already exactly what it's going to be. It's the same punchline. In a child, as opposed to a fetus, chronic activation of the stress response does all sorts of bad stuff. And it's in a very similar realm, very similar sorts of punchlines. If you stress an infant rat, stress not by nutrient deprivation, so in this case, you're not producing a Dutch hunger winter effect, stress in all sorts of different possible ways, and you produce an adult rat with higher glucocorticoid levels. An adult rat who has trouble turning off glucocorticoid secretion at the end of stress, a rat with a somewhat activated stress response all the time when there's nothing stressful going on. A rat more vulnerable to a bunch of those diseases. You get a rat who is not as good at learning and memory, whose brain in the cognitive realm hasn't developed all that well. You get a rat that is more prone towards anxiety. You get a rat that has fewer of those benzodiazepine receptors in there. You have parts of the brain like the hippocampus, which does not develop as normally. Stay tuned. We'll hear plenty about that. You've got all sorts of these long-term consequences. The same sort of picture there. Now, what this begins to bring in is something even more subtle. First question that one might arise when grasping all these prenatal and postnatal stress effects is, well, how much do I have to worry about it in terms of, is this a Dutch hunger winter phenomenon? Everybody who has a fairly normal diet as a fetus, everything is fine, and it's only at the extreme that suddenly you get this increased metabolic risk. No, what you see instead is across the whole normal range of prenatal nutrition, across the whole range as manifested in birth weight as a percentage of body length, this is not just about the extremes. So once you recognize that it's not just about these extreme states, but instead the whole array of developmental stressors, moderate, medium, severe, all of that, the whole array of prenatal effects, suddenly you realize there's something that's got to come into the equation, which is mothering style. Different styles of mothering can represent and generate a more stimulatory environment, a less, a more stressful, all of that. And suddenly you've got this whole issue of, does mothering style have an influence on the nature of metabolic programming, what sort of stress response the offspring has an adult? And there's been some wonderful work done on this by lots of investigators. One of the leading ones, named Michael Meany at McGill University, fabulous scientist, and also an old friend and collaborator, who gave a very modern spin to a time-worn phenomenon in this field. Take a newborn rat, and over the first couple of weeks of its life, pick it up every day and handle it. Pet it for a few minutes. Take it away from its mom for a few minutes and then put it back. Do that every day for 3 minutes or so, and what you have now done is neonatally handled that rat. And what this counts as is stimulation. And remarkably, this is now a rat who, as an adult, will have lower glucocorticoid levels, that will have better learning and memory, as it turns out, will have a more neurologically intact old age, the right amount of stimulation. Meanwhile, do something else, pick up a rat and pet it and put it away from mom for 180 minutes, for 3 hours rather than 3 minutes, and then bring it back to mom, and you now produce an adult with a hyperactive stress response, an impaired cognition, and what you see is it's the exact same stimulus, maternal deprivation and tactile stimulation. 3 minutes, great thing. 3 hours, terrible thing. What we will come to in later lectures, where's the transition from stimulation to stress? So this very well-established phenomenon, this neonatal handling business. Now, when you stop and think about it, whatever's going on inside these baby rats did not evolve in order to give grad students doctorates out of petting rats 3 minutes a day. What's the equivalent in a rat's real world? And what Meany first showed was this translate into mothering style. You take the baby rats away from mom for a certain length of time, and you bring the rat back, and mom changes her behavior. And what you see is when the baby's away for only 3 minutes, mom becomes more attentive. She grooms the baby more. She licks the baby more. Take the infant away for 3 hours, put him back with mom, and there's a certain degree of detachment that goes on then. Mothering style, what this handling phenomenon is mostly about, is what sort of maternal behaviors are elicited when you return the pup. Meany then took it one step further. Forget this, taking the pup out of the cage and petting it and taking it away from mom for differing lengths of time. Now, just do something much more straightforward, which is look at the style of mothering. What's the normative range of mothering among rats? Remarkably enough, some rats are more attentive moms than other rats. The normal range of variability applies to all sorts of other species. Absolutely straightforward. Some rats lick their pups more than other rats do. Some rats groom their babies more, some groom them less, some are more or less physically rough with them, more interactive, all those sorts of things you can imagine. And what they see in their studies is the extent to which there is maternal licking and grooming will cause programming in adulthood. Get a mom who does an optimal amount of licking and grooming of her baby rat there, and she produces an adult with lower glucocorticoid levels, better learning and memory, all that sort of stuff. So that's absolutely remarkable. And it turns out that there's all sorts of ways in which rat mothering style translates into a different adult stress response in the offspring. Turns out to work the same way in non-human primates. And that can take all sorts of forms. Very simple sort of one. How anxious of a monkey mother do you have? What does anxiety in a mothering style look like in a non-human primate? Baby gets up and goes walking to start exploring the world. How far away from mom can it go before mom reaches over and grabs her kid and yanks them back, saying, the world's not a safe place when you get this far from me. And anxious monkey mothers, the kids go a tiny difference before mom communicates anxiety and, ooh, it's scary, come on back. And less anxious mothers even further away. And that translates into different stress hormone levels. That translates into different adult profiles of stress responses. Absolutely amazing. So we've now seen a couple of remarkable things here. One, environment doesn't begin at birth. These really long-term, persistent effects on physiology, on disease risk as a function of fetal stress experience. And we've now seen very similar sorts of themes in postnatal experience while growing up. And what we see is this is not just about extremes. This covers the range of differences in stimulation and stress that's encompassed even in differences in mothering style among rats and monkeys. Now, what's become a huge question in the field, a huge challenge, and one which, has to be in there the second you start thinking about stuff working this way, is how does it work this way? How do you translate how much a mother rat licks her pups into what sort of glucocorticoid levels those pups are going to have in their old age in some cases? How does that work? And that is an extraordinarily tough problem to try to make any headway with, because this is not obvious. How does licking turn into a different hypothalamus or perhaps pituitary adrenals? How did this stuff work? And this is where Meany and his collaborators have come up with some extraordinary findings. This whole new area of molecular biology, close your ears if this is more detail than you want, but this whole new field called epigenetics. You got genes which direct the construction of certain proteins, and when a gene activates, it generates a certain protein that it codes for. That's great. Genes as determining the workings of the entire universe. When does a gene know when to activate? And it turns out in your DNA, not only are there lots of genes, but there's on and off switches. Things in the outside world that will activate a particular gene to produce its protein product, all that sort of thing. And it turns out epigenetics, what epigenetics is about is early experience can cause a permanent stage of a switch being held on all the time or being held off all the time. And what Meany pioneered in showing is that mothering style causes certain epigenetic changes in the brain having to do with what sort of glucocorticoid levels there'll be in adulthood. It's still not clear how you get from licking to this epigenetic stuff. The nuts and bolts are getting worked out these days. How you do that, but at least it's understood now how differences in prenatal, postnatal experience produce propensities towards certain genes being more active than others or less active. Remarkable finding in the last few years. Go to those Dutch hunger winter adults, the human ones, and look at certain key genes in them, and there have been those epigenetic changes. What sorts of genes, not genes coding for eye color or how wide their feet are or anything, genes having to do with insulin actions. Perfect, exactly what you would expect. So what we see here is the way in which experience, prenatal and postnatal, can shape the sort of hormonal profile you have as an adult, the sort of brain you have, early experience taking the form of severe stress, but also mild stress, and degrees of stimulation and mothering style, producing different profiles in adulthood, producing, as we saw most remarkably, even profiles in the next generation and the next. Okay, it's right around this point where if you are a parent, you grind to a screeching neurotic halt because, like, here's a whole new realm in which you can screw up your kids. Okay, I have to do something confessional here, which is tell you a few of the ways in which my wife and I have been horrible, horrible parents. There was the time when my wife was pregnant with our first child, our son, during the third trimester, where we went to what turned out to be a really loud concert, and right in the middle of it, our son kicked. And we said, oh my God, we're stressing him, this auditory environmental stressor, we have screwed up. Then there was the time that we meant to put on some video, one of those great educational ones, like a video for 4-year-olds about plate tectonics or something, and we messed up with the machine, and for about 15 seconds instead there was some horrible, violent cartoon, and we messed up. Then there was the time, in order to placate my second child, our dog, we actually let her have some sugary cereal. Oh, we have messed up forever. We all know that neurosis. The notion that do something wrong with your child and there will be long-term consequences. Oh my God, that's crazy. You got to get this stuff under control. And then along comes this whole field saying experience, remarkably subtle differences in experience, beginning as a fetus, produce the sort of adult you will be. Produce perhaps even the sort of children you'll have, these long-term effects, these fetal origins of adult disease. So suddenly you get that much crazier as a neurotic parent. Look at the ways in which early experience has long-term consequences. Okay, so in response to all this neurosis, there's some bad news and some good news. Some of the bad news you've already heard, which is this a world only of extreme adverse experience versus everything else you get a pretty normal outcome? No, we just saw that this covers the whole normal range of variability, amount of prenatal nutrition mapping onto adult metabolic profiles. So this is not just about them and their horrific parenting and prenatal lives. This is something that appears to apply across the whole range of development. Next source of bad news, which is how big are these effects? If you're sort of a mainstream medicine type and you hear about stuff like this, the first response is that's ridiculous. There's no way stuff can work like this. And then when it is shown, yes, there are prenatal programming effects. The next sort of thing you do to kind of deny the importance is say, yes, okay, I give up, it's for real, but these are not big effects. These can be enormous effects. The Dutch hunger winter phenomenon, as I mentioned, be a prenatally stressed Dutch fetus during that Dutch hunger winter, and your increased risk of metabolic syndrome, obesity, hypertension, diabetes, your increased risk 50 years later is not a tiny effect, it's almost a 20-fold increase. So we got bad news. Normative range of developmental experience produces a normal range of better or worse adult profiles, and these are big effects. These are not little hiccups of biology. But now the good news. How inevitable is this to occur if you were stressed prenatally for 3.5 minutes, you're going to pay a price? No, there's enormous amounts of variability from one individual to another. Developmental stress does not guarantee that you are up the creek in that way. And the other piece of good news is, are these things permanent? Prenatal stress, and suddenly are you guaranteed to have a miserable hyperglycemic 80th birthday? No. What's also clear is, amid the persistence of these effects, there's a tremendous capacity to reverse them throughout life. Okay, so we got some pluses and minuses. Now, as you think about this, what's the undercurrent of all this parental anxiety of, did I do too much of this and too little of that, and all of this nutsiness? What's intrinsic in all of that after a while is, what's the optimal parenting style? And this is a domain of complete craziness. And you get some interesting insights into it when you look at work of, say, anthropologists who look at mothering styles as they vary cross-culturally. And there's differences. There's dramatic differences across cultures. How much physical contact does a baby spend with its mother? How much physical contact with non-mothers? How long on the average does a baby cry in this culture before it's picked up? At what age do babies stop sleeping with their mothers? Tremendous variability in that. So you look at this and suddenly you are thinking, well, if I can only learn enough about these cross-cultural patterns, I could come up with the perfect mothering style, which will have like the Trobriand Islander diet and the like a Turi Pygmy preschool curriculum and the Kwakiutl exercise regime, and it doesn't work that way. An anthropologist at Cornell named Meredith Small wrote a wonderful book that gets at this issue. And you look at all of the variability in parenting style across cultures, and what you realize is there's no optimal style. There's no style that is most natural, most embedded in our hominid history. What we do in culture after culture is we raise children to become the sort of adults that we value. And what you wind up seeing in our own society and our own culture is an example of this, one perfectly captured by this old Harry Chapin song, Cat's Cat in the Cradle, which is this yuppie and baby boomer song of middle-aged regret, which is, "My boy grew up just like me."
Lecture 7. Stress, Growth, and Child Development.
Well, we're back. I've got on a new pair of socks and I'm freshly shaved, so ready for more. Part 2 of Stress and Growth. Now, you'll remember the main point of the previous lecture, amid our logic, chronic stress, bad news for growth, was the fact that environment does not begin at birth, that whole world of prenatal stress, that whole world of prenatal programming of adult metabolism, that was last lecture. What we'll emphasize here is growth not by way of signals from mom, but growth as experienced by the organism itself by way of stress. Okay, we know the logic once again, running away from the lion, blah, blah, chronic stress. How does this get turned into effects on growth? Because what you get after a while is precisely what seems logical, which is if you are a young organism and you are chronically stressed, you're not going to grow as fast. This is different from last lecture, chronic stress early in life, and when you're 70, things will be working differently. This is just the plain, straightforward world of lots of stress, and a kid doesn't grow as much. So what are some of the mechanisms underlying this? Some very straightforward ones, and ones that you could probably construct from Lesson 2, from the second lecture, going over the building blocks of the stress response. Very simple. Those elevated levels of glucocorticoids, that elevated activation of the sympathetic nervous system, the decreased secretion of growth hormone, put those together and that's where you've got problems with growth. Another one as well, remember the cardiovascular stress response. Not only do you want your blood pressure to go up to deliver energy to those thigh muscles, but in addition, you don't want to deliver blood to unessential areas, like your gut. We saw in the previous lecture how one consequence of that is if you are chronically stressed and chronically decreasing blood flow to your gut, it's more prone towards an ulcer. That whole picture. What we see here is if you were a kid and you were chronically decreasing blood flow to your gut, you're not absorbing nutrients as readily. So that's another mechanism by which you can disturb growth in kids thanks to chronic stress. Now, another question that seems to come up here over and over as we look at some of these adverse outcomes, how big of effects are these? Ooh, thanks to enormous amounts of childhood stress, you're 1/8 of an inch shorter than you would have been otherwise. No, these are not small, subtle effects. And at an extreme, you get one of the truly bizarre, disturbing outposts of medicine, a disease of kids who are so stressed that they stop growing entirely. Termed stress dwarfism, also known as psychosocial dwarfism, psychogenic dwarfism, and this is for real. This is a child where there's no obvious disease, there's no malnutrition, there's no parasites. You look in the bloodstream and there's no growth hormone. You give them synthetic growth hormone, nothing happens, the whole system is shut down. And what you have here are the consequences of truly sustained adverse stress. You check around with that kid's background, and out comes some appalling psychological stressor. And this is standard textbook knowledge. Get some textbook of endocrinology, look in the chapter on growth, and I guarantee you somewhere in there will be the obligatory picture of the stress dwarfism kid. You know those pictures, this is, the stunted kid who's naked in front of the growth chart with a rectangle over the eyes, and then I guarantee you turn the page and you see the consequence of removing that child from that stressful setting. Technical term, you do a parentectomy on them, get them into a different setting, you turn that page, and there's the same kid 2 years later, and they're like 6'14", and they're playing for the NBA, and they're still naked with a rectangle, but everything else gets better. What we see here is the profound capacity of stress to disrupt growth and the remarkable capacity to recover from it. One dramatic example, and this was a paper that was published a few years ago about a child with stress dwarfism who wound up in New York Hospital, a child from a severely stressful psychological setting, and they showed when the child came into this pediatric ward, growth hormone levels were like at the floor. Over the next 3 months, he developed this close relationship with this one nurse. This was like the first normal emotional relationship of his life. By the end of those 3 months, he had perfectly normal levels of growth hormone. At that point, nurse goes on vacation. By the end of the 2-week vacation, the boy's back down to virtually zero. Nurse comes back from vacation, bounces back up. Think about it. Think about it, the rate at which this child was depositing calcium in his bones could be predicted by just how loved and safe he was feeling in the world. You can't ask for a much better example that what's going on here affects every outpost in the body. So we have stress dwarfism. The question then becomes one of magnitude, one of frequency. How common is this disease? If you are shorter than average and you were not obviously malnourished as a kid, are you a victim of stress dwarfism? That's something else your parents did to you? No, this is not conventional stress. This is not, ooh, when I was a kid, we moved all the time, very stressful. This is not acrimonious divorce. This is nightmare psychopathology. This is the police and the social workers breaking down the door of the apartment and finding the child chained to the radiator, smeared in excrement, total nightmare stuff, and remarkably, get the child out of that setting and there is recovery. And the general consensus in the field is this is a remarkably rare disease. This is a once-in-a-career disease to see, extremely rare. Except it's not so rare. It pops up all over the place. It pops up in areas of, perfectly logically, extreme stress. For example, a whole literature emerging about these poor kids who were raised in the Romanian orphanages shortly after the fall of communism there. And this was just the nightmare settings of kids like warehoused in these orphanages with incredible absence of stimulation and contact and affection, all of that. Major impairment of growth. Okay, so that's one disturbing realm. But it pops up in other places as well. Here's a great historical factoid. King Frederick II of Sicily, some 13th century despot who clearly was, an early pioneering endocrinologist. I don't know what was going on in their court, but one day they were sitting around there having this argument about what's the natural language of humans. Presumably there was no villages to pillage and loot or whatever, so they were doing philosophy instead that winter, and what's the natural language? And they were holding out one for Greek and another for Latin or classical Hebrew, and presumably Frederick II of Sicily was holding out for Italian, and he did what was for the time a remarkable experiment. He got some children. He commandeered some children in his kingdom, and he had them raised in complete isolation for a number of years. Isolation like no one talking to them. like whoever's giving them food runs in silently and leaves food for them, minimal contact with other humans. And the notion in this experiment was, at some point, they're going to open the door and out will come the child reciting in classical Greek or whatever it is, the natural language of humans. And eventually they opened the door and the kids did not come out speaking classical Greek. The kids did not come out at all. They had died from the extreme of stress dwarfism. So more examples of that, more examples where this comes up. Amid this picture of, oh, this is only at the great extremes, what you've got instead is a lot of cases where it does occur. One example, kids who grow up in areas, war zones, areas of civil strife, kids who grow up with all sorts of family dynamics that are highly stressful. Here's one really interesting example. This was a classic study done by a pair of anthropologists in the early 60s, looking at kids from different cultures and asking how physically stressful are the rites of passages in this culture. Rites of passages, in some culture they scarification or piercing of body parts or tattooing or putting you out in the desert with poison ants. And in some cultures, you have to play the piano for your grandmother and her friends, whatever's done in your particular tribe. They did like 80 comparisons. They controlled for genetics. They did this perfectly. And what they showed was highly physically stressful rites of passages between ages 6 to 15 or so, 1.5 inches shorter as an adult. Let me tell you about the single creepiest example of stress dwarfism I've ever heard of, and if this doesn't unnerve you, you've got no imagination at all. Here it is. If for some inexcusable reason you find yourself reading chapter after chapter about growth hormone, you're going to find this weird pattern, which is a lot of these chapters make reference to Peter Pan. Peter Pan Peter Pan, quotes from Peter Pan, snide comments about Tinkerbell. I'd seen this for years and I had no idea what was going on. Until one day, I'm reading a chapter about stress regulation and growth and the possibilities for stress dwarfism, gave the following case history, which is 8-year-old boy growing up in Victorian England. Perfectly comfortable middle-class family in the 1870s. One day, he sees his beloved older brother killed in front of him in an accident. This destroys the family. There were no other children. The father was emotionally non-existent. This was the mother's favorite child in this Victorian swoon. She takes to her bed with the shades drawn for the next 10 years or so. Here's this child growing up in this complete emotional vacuum. And there's these terrible scenes where he brings in a tray of food for his mother and she's saying, "Oh, David, is that you? David, if you come to me, David, the dead son." And she'll go on, "Oh, David, are you finally?" Oh, it's only you. Growing up being only you. Apparently one of the only things that the mother ever talked to him about was this crazy idea that she grabbed onto, which was, if David had to die, he died when he was still my perfect little boy. He never grew up into a man who doesn't need his mother anymore. He'll always be my perfect little boy who didn't grow up. This kid hears this with a vengeance. No evidence of malnutrition, no evidence of disease, stops growing at that point, lives to 60 years of age, under 5 feet tall, dramatic effect, unconsummated marriage, and this winds up being a wild example of stress dwarfism. And then the chapter concludes by informing us that as an adult, this was the author of the much beloved children's classic, Peter Pan. This was J.M. Barrie, the author of Peter Pan. This was one incredibly messed up guy. This was a guy who just cranked out plays after novellas about boys who die and come back as ghosts and marry their mothers and all sorts of stuff like that. His private journals were full of sadomasochistic fantasies with little boys. This guy spent the rest of his life not very effectively dealing with his stress dwarfism. So you may want to think about that the next time you see Johnny Depp up on the screen. But that's a case of one. That's a sample of one. What's the experimental evidence? Another remarkable example, a textbook example, where if you were working with lab rats, you could not have designed a better experiment. And this was in an orphanage in Germany shortly after World War II. A series of orphanages, in fact. And what was noted was the children in one of these orphanages had a very stunted growth rate compared to the other ones. And people went and studied, and what they thought might have been relevant was the woman running the orphanage, who was this cold, berating woman who had like zero physical contact with the kids. Okay, that's a nice speculation. Now what was done was the sort of thing that you could not have done any better with the rats. The woman was transferred to a different orphanage. And suddenly, the growth rates in that orphanage went down. Remember, everything's controlled for the kids in all these orphanages are getting the same diet, the same number of doctors' visits, the same vaccinations. All that was different was this woman in charge. One additional wrinkle, which was, and she moved her favorites with her to each orphanage she was assigned to, and those favorites grew at a normal rate. This is a classic example, another one of those that winds up in every textbook. So based on this, suddenly there's all sorts of possible therapies that come to mind. And a remarkable one was worked out a few decades ago by a psychologist at the University of Miami named Tiffany Field. And what she did was notice one of the high points, one of the triumphs of modern medicine with a very major downside, which is you look at kids who wind up in NICUs, neonatal intensive care units, and they are taken care of in tubes and tests and monitors and all sorts of things. And in the process of that, there's one thing they don't have, which is a whole lot of physical contact with people. And Field came up with this idea, how about we go in and physically stimulate these preemies, these severe preemies? How about we go in and massage their backs? Massage their backs. How do you massage the back of a tiny preemie? You're doing it with your thumbs. And they went in and they did it 3 times a day, and they discovered something remarkable, which was there was about a 50% increase in the growth rate in the preemies who were stimulated in this way. The babies were more alert. They were more active. They went home at an earlier stage. And looking at them months later, their growth rates were still enhanced. This was a remarkable effect. And Field and the sort of people who have followed up on her work have done some estimates that if this were done in every neonatal ward in the country, it would save a huge number of lives. It would save billions of dollars in terms of the long-term adverse consequences of being an extreme preemie. A remarkable demonstration that get just the right amount of stimulation and growth is enhanced. Just as we've been seeing, get the wrong amounts into the stressful range and you disrupt normal growth. Now, all of this is about kids, but somewhere in there, we've got to think about adults, because by now I've noted growth hormone. Growth hormone has popped up a whole bunch of times in this course so far, and growth hormone, you secrete less of it during stress, all of that. What does growth hormone do? It makes you grow, which is what kids are about. But you look at adults, and they've got plenty of growth hormone in their bloodstream. And most of us as adults, we're not growing anymore other than wider as the years go by. What's growth hormone doing in the adult? And it turns out a very special role that at first was thought to have nothing to do with stress, but where the jury might be no longer out on this, which is what you do with growth hormone is remodel your bones. Now, most of us view bones as totally boring and nothing's happening there, and they just kind of keep your body together and bipedal and stuff like that. Bones are extremely dynamic parts of the body. You're putting in calcium, you're taking it out, you're remodeling. I mean, how else does somebody get bow-legged if you're not constantly remodeling your bones in response to the world around it? So what's doing the remodeling? You pull calcium out, you put it in. Growth hormone plays a huge role in depositing new calcium into bones. So along comes chronic stress, and it's not that you're a kid impairing growth, you're an adult, growth hormone levels drop, and what might be the consequence of that? You are now depositing less calcium into your bones. So what's that going to set you up for? Brittle bones, prematurely aged bones, osteoporosis, and suddenly, in the realm of stress-related disease, there's this possibility that chronic stress can increase the risk of osteoporosis. Now, what the consensus was in the field until some time ago was, yes, this is possible, but this is not likely to occur. You need such extremes of adult stress and such a collapse in growth hormone secretion that you never actually get overt osteoporosis. You may get the first little baby steps in that direction, but nonetheless, this is not a realm of stress-related diseases you need to worry about. And some years ago, it became clear that this wasn't the case. And this was work done by Carol Shively and Jay Kaplan at Bowman Gray Medical School, and they showed that there was a tragic, confused flaw in the whole biomedical literature built around doing this. And the flaw was as follows: the tendency of scientists to study male rats and male monkeys and male college students, and they're not all that representative of what animals are about, what humans are about, because it's losing half of the equation. Overwhelming the literature was built around studies of males. Now, what happens when you're male and you're chronically stressed? As we know by now, up go glucocorticoid levels, down go growth hormone levels. And what does that wind up doing? Up increased glucocorticoid levels, you're pulling a lot of calcium out of your bones. Low growth hormone levels, you're not replacing it, and as we've seen, put those pieces together in the male rats, monkeys, etc., and you get just a hint of osteoporosis. Chronically stressed females, and something else happens. You've got the elevated glucocorticoid levels, you have the suppressed growth hormone levels, but as we are going to find out in the next lecture, something else gets suppressed, which are levels of estrogen. Now, amid all the controversies of hormone replacement therapy with estrogen postmenopausally, one thing that is absolutely clear is estrogen is very good for the health of your bones. Estrogen promotes calcium uptake. Estrogen is terrific in that regard. It decreases your risk of osteoporosis. That's great. So with females with chronic stress, instead of two things going wrong that puts you within the ballpark of osteoporosis, three things: elevated glucocorticoids, low growth hormone, and low estrogen, and suddenly you're more at risk for osteoporosis. At this point, the work of Shively and Kaplan have shown that this is precisely what's going on in lab monkeys and experimental monkeys, females with chronic stress, manipulating estrogen levels. Not quite clear in humans yet. The work is still going on in that area. Okay, so we've had this whole range of possible ways in which things can go wrong: prenatal stress, postnatal stress, effects on growth, how long-term are they, how common are these disorders of blunted growth in response to stress, what can be done about it perhaps, Tiffany Field studies of intervention with extreme preemie kids. Lurking around in all of this here is the same sort of theme that was lurking around in the previous lecture, which is parenting style. And how does parenting style wind up influencing the growth rate? And for this, one has to get a sense of history and the history of what sort of parents have been advised to be. And for a gazillion generations, all of us grew up under the advice of Spock, Dr. Spock. Back around 1900, there was a different person who was the expert, a man named Luther Holt at Columbia University. And Holt was the most influential expert at the time, teaching parents about parenting. And what he had to say was very different from a Dr. Spock scenario. He was the person of the school of spare the rod, spoil the child. Children are meant to be seen and not heard. He even used phrases like referring to the vicious practice of picking up babies when they were crying and advising parents not to do that. This was an extremely stern view of what parenting should be. This was the dominant model at the time. And a number of decades later, with this remaining as the dominant model, along came a man who absolutely revolutionized this field, a man named Harry Harlow. Now, to appreciate what Harlow accomplished, you have to consider what were some of the dominant schools of psychology at the time. In addition to this whole view of people like Holt of very stern, detached parenting styles, there was this school of psychology that dominated American psychology in the 20th century, the field of behaviorism. best personified by the most famous behaviorist of all time, B.F. Skinner of Harvard. And in a totally simplified way, what was behaviorism about? You get rewarded for something, you're more likely to do it later. You get punished for something, you're less likely to do it. Positive, negative reinforcement, those are not exactly comparable to reward and punishment. Nonetheless, this general world of behaviorism, things that have good outcomes, you're more likely to do afterward. Things with bad outcomes, less. So what would behaviorists have to say about this whole maturational process amid Luther Holt type advice? Somewhere up there comes this question, why do kids wind up getting attached to their mothers? Why do kids bond to their mothers? And you're a behaviorist and you had the exact answer, which is you get attached to mom because she feeds you. You get positively reinforced. You get reinforced in those circumstances where you're sitting there saying, my gosh, I'm feeling a little bit hypoglycemic, and here's this breast belonging to mom, and soon I'm not so hypoglycemic. Why? I'll begin to have all sorts of positive feelings about this individual. That was the behaviorist view. Why do we get attached to mothers? Because mothers supply this essential need for nutrients. That was the dominant thinking at the time. And all you have to do is combine that with the sort of thinking in the Holt school of parenting style, and you come up with some pretty stern views, which is basically, as long as you provide a kid with food and adequate warmth and things like that, that's all you need to do. And remarkably, this dominated pediatrics at the time, hospital policies, pediatric boards, something that is inconceivable these days, which is your child winds up with some illness and is in a pediatric ward for a few weeks or so. And what was the rule at the time in most of these hospitals? Parents were allowed in for a few minutes a day. Perhaps parents were allowed in only for an hour a week, because after all parents do is mess up the process with the vicious practice of picking up their kids and coddling them. And what we've learned from Skinner and learned from the likes of Luther Holt is supply food, supply the right number of blankets, and that's all you need to do and be doing things correctly. So here comes the Harlow Revolution. Here's where this critical experiment was done that transformed how people think about this subject. One that winds up in every single textbook. I can almost guarantee you've seen one of the pictures from this experiment if you've ever taken Psych 101. This was this classic, brilliant experiment that Harlow did. He takes baby monkeys being raised without a mother, a biological mother. And what they're raised with instead are two different types of surrogate mothers, substitute mothers for a real monkey mother. The first one was a tube of chicken wire with some styrofoam monkey head looking thing up on top and a bottle of milk sticking out of the chicken wire torso, roughly where the breasts are. Second surrogate, a tube of chicken wire with a monkey head on top and no milk, instead a warm terry cloth wrapped around the torso. So you ask the question, which of these two surrogate mothers is a baby monkey going to get attached to? And if you're B.F. Skinner, it's completely obvious what the answer is, and you would expect Skinner to very quickly be clutching the chicken wire mom with the baby bottle there, because that one supplies nutrients. And of course, you get attached to mom because she supplies you with nutrients. Look at a real living primate. Look at these baby monkeys, and they did something very different instead, which is, sure, they were willing to go on the chicken wire mothers with milk. They needed milk. Who were they attached to, though? Who did they spend most of their time on? Who, when something scared them, did they go scampering to for comfort? The warm mother with the terry cloth. It's not that you get attached to mom because she gives you an adequate number of calories. You get attached to mom because she makes you feel safe and makes you feel beloved. And what Harlow did was introduce a word into the technical scientific literature in his papers, the word love. You get attached to mom because she supplies things that are so much more important and fundamental and interesting than adequate calories and, keeping your body at the same temperature that it's supposed to be. And out of Harlow's work came enormously important elaborations. One, a study, for example, that showed just how wrong the behaviorists were. Here, you've got the cloth mom, which a baby monkey is happy to hold on to. And what you've got is, in the middle of the torso, was a little spigot that could blast out, very briefly, a jet of air. Unpleasant. And not something you would want to stick around for if you're a behaviorist. And the rule that was set up was, when you clutch onto the torso of the mom, you get a blast of air coming out of the torso. Any behaviorist would have predicted at that point that what the baby monkeys are supposed to do is they stop clinging. And what they did instead makes perfect sense to anyone who has grown up and attached to anyone. The more they got blasted with the air, the harder they held on to mom. There's no positive, negative reinforcement world there of, oh, you get unattached to individuals who blast you with jets of air. What we have here is remarkable insight into things like, why do we love people who mistreat us? Why do we make the wrong choices in that realm? And it's got to do with what it is we attach to. And what Harlow showed was, it's not about calories, it's about comfort and safety and love. Now, Harry Harlow's work has wound up being enormously controversial. And this was a man who has been just vilified in certain circles of research because he did elaborations on these studies that were brutal. Monkeys being raised in complete social isolation, monkey models of severe psychiatric disorders, extremely brutal stuff. And when I was a student first reading Harlow's work, I was horrified by some of it, not only the experiments, but an extremely callous style that he had in his papers. I was moved to tears by some of these studies, how awful they were. And perhaps relevant or perhaps not, Harlow sank into eventually fatal alcoholism amid all this, a very troubled man who did often some very troubling experiments. And you look at them and you ask what seems to be a perfectly obvious question: didn't they know it worked this way? Didn't they know that baby monkeys, if raised in isolation, would wither away? Wasn't it obvious? Ironically, it took Harlow's work to show how unethical his own work was. You look at a baby monkey and it's perfectly obvious what would happen if Harlow socially isolated them without a mom. If you prick us, do we not bleed? If you socially isolate us, do we not suffer? The point of Harlow's work was not that it showed the obvious, which is if you socially isolate a monkey in early life, it's going to suffer. What he really showed was if you do the same thing to a human, the same thing happens. And that sure wasn't obvious at the time.
Lecture 8. Stress and Female Reproduction.
Well, we are back again. I have a spanking new set of clothes, courtesy of the teaching company, all the way down to new socks, so I am just brimming with manly self-confidence, and thus am willing to tackle the issue of stress and female reproduction. Now, of course, you know the drill by now, which is going to be short term, running away from the lion, 30 seconds, got better things to do than thicken your uterine walls, long-term problem, chronic stress, and you begin to impair the reproductive system. Now, starting off, a great way to appreciate just how much this is one of those indulgences, reproduction, one of those ones that fall under the auspices of big, expensive, long-term, optimistic, and this is no time for it, is to appreciate just how expensive some aspects of female reproduction is. Best estimates are 50,000 calories that you go through over the course of a pregnancy, about 1,000 calories a day nursing, and this is simply something that's very tough to afford when you're running for your life. And in the face of chronic stress, this is the sort of realm that gets greatly impaired. And of course, you know where we go next with this, which is chronic stress in the form of psychological, psychosocial. It makes no sense at all for your body to say, oh my God, this is too expensive, let's defer until another period. Once again, you have that same logic that has haunted us in terms of stress-related disease. Real physical stressors, the stress response is wonderfully adaptive. Psychosocial stressors that we humans specialize in, and it makes no sense to turn on the chronic stress response, and this is one of the realms where you pay a price. Now, to appreciate it, we've got to tackle one of those endocrine axes, as talked about in the second lecture, have to tackle one of those pathways, which, as you'll recall, starts with the master gland, your brain, releasing a hormone that has an effect at the pituitary, which then, in this case, has an effect on the ovaries. Now, it's actually two different sets of hormones that wind up being relevant here. The first one, for the first half of one's reproductive cycle, known as the follicular stage. What you're doing there is you're maturing follicles. You're maturing eggs that will be released around day 14 of the cycle, and then you transition to what's called the luteal phase. Notion being, if conception occurred right around that 14th day, plus or minus a couple of days, what you now need to do is prepare your body, your uterus, for starting a pregnancy, implanting this fertilized egg. So what are the hormones involved? Follicular stage, that same axis again as promised, brain, pituitary, peripheral glands. You have, starting off, a hormone that lots of people are familiar with, coming out of the pituitary, luteinizing hormone. Luteinizing hormone, once again, do not write these down, do not panic if you don't know these terms and don't want to learn these terms. You got a hormone that comes out of the pituitary, which is going to stimulate egg maturation. And of course, what you know is the pituitary hasn't a clue when to release luteinizing hormone under the control of the brain, the hypothalamus, which releases the bizarrely named luteinizing hormone releasing hormone. So out comes this LHRH from the hypothalamus, has an effect on the pituitary, out comes LH, and you are now causing preparation for fertilization. You also are releasing follicle-stimulating hormone out of your pituitary, and collectively what LH and FSH are doing is maturing eggs and producing estrogen coming out of the ovaries plays a critical role in that. Now, once you transition over to the luteal phase, a different hormone dominates, and that's known as progesterone. And all you need to do to get a sense of what it's up to is progesterone progestational. What it does is prepare the uterus, thickening it, preparing it for implantation of the fertilized egg. Okay, so we've got all the basics of the system under our belt here, and what we now transition to, of course, is what's occurring during stress. What's occurring with this hypothalamic pituitary gonadal axis. Now, what you see is a very complicated version of exactly what we know by now. First thing that happens, remember that hypothalamic hormone, luteinizing hormone, releasing hormone, the first thing that happens during stress is it releases less of the stuff. And that's occurring within seconds. Which hormones are responsible for that? You remember some of the dread names from earlier on, glucocorticoids. Glucocorticoids work up in the hypothalamus to inhibit the release of LHRH. Another hormone is relevant there, one that was mentioned for 1.5 seconds in that prior lecture, which now begins to be relevant for the first time, that hormone beta-endorphin. Beta-endorphin, about the only thing that sort of registers with most people about beta-endorphin is it's got something to do with blocking pain or runner's high, endorphin high. What's it doing instead working at the hypothalamus to block LHRH release? Very few hormones do only one thing. So this is another function of beta-endorphin. Don't panic. Do not write these down. Again, get the general theme. So we've got the first thing that happens, which is decreased hypothalamic, decreased brain release of this LHRH. And by all logic, what that should now do is have a consequence at the pituitary. For lack of that LHRH stimulation, the pituitary is now going to be releasing less LH and FSH. But that's not enough. Your brain does not trust that things can be solved merely by shutting off LHRH secretion. Another thing that happens is you send signals, hormonal stress signals, you send signals to the pituitary to make it less responsive to whatever LHRH is coming out. And you could probably guess the mechanism by now. Just like every other hormone, LHRH works by way of its receptor in the pituitary. The pituitary starts making less of these receptors. So you've got a double whammy there. Less of the signaling hormone is coming out of the brain, and the pituitary is less sensitive to that. So we know the consequence there already. There's going to be less LH, less FSH coming out, and thus the ovaries are going to be less stimulated to release estrogen. And once again, the same theme, just in case the pituitary is screwing up and still releasing some of that LH and FSH, the stress response, heavily glucocorticoids, are working down at the ovaries to make them less sensitive to LH and FSH. And you guessed it, there are LH receptors in the ovaries and FSH receptors, and there's fewer receptors. So you've got less of the hypothalamic hormone, and the pituitary pays less attention to it. You've got less of the pituitary hormones coming out, and the ovaries pay less attention. And the result is lower estrogen levels and less likelihood of fertilizing an egg. Now, the next thing that kicks in is less progesterone. That's another step in the pathway. Those same stress hormones and the same ones begin to pop up over and over. Glucocorticoids, beta endorphin, they're also blocking the release of progesterone. And what you've got at this point is not only were you not releasing LH, FSH, estrogen, and maturing the eggs, but just in case against all these ridiculous odds, you somehow managed to get an egg that matures sufficiently through this follicular stage that it actually gets fertilized. What you've now done is you are making sure the uterus is not matured enough for this fertilized egg to implant. And the way you do that is exactly what we were just talking about. You secrete less of that progestational progesterone. You don't thicken the uterine walls, and it's less likely that the rare fertilized egg is actually going to implant there. One additional hormone that's going to become very relevant soon has a role in that, a hormone called prolactin. And we're going to see all sorts of things that prolactin does. One of the things it does in this case is it counters the effect of any progesterone that you still manage to dribble out despite the stress signals. What prolactin also does is thin out your uterine walls. So what should impress you by now is this is an incredible number of mechanisms for shutting down this reproductive ovarian axis at the level of the brain, the level of pituitary sensitivity, the brain signal, the pituitary ovarian sensitivity, all these steps. There's one really interesting additional step that comes in there, and it's got to do, oddly enough, with fat cells in females. And it's got to do with a very, very unlikely thing that females do, including human females, which is they secrete a certain amount of male sex hormones into the bloodstream, androgenic hormones like testosterone. Where are those coming from? From the adrenal glands. Remember, what the adrenal glands are up to is making adrenaline, epinephrine, glucocorticoids. In females, bizarrely, they also make adrenal androgens. Not a ton of this stuff, maybe 5% the levels you would see in a male. Nonetheless, you got to get rid of this stuff. Unfortunately, as I noted there, fat cells come into play here, which is fat cells have this enzyme that could do like biochemistry 101. They could take the circulating testosterone and convert it to estrogen. That's great. Everybody lives happily ever after. You've turned these bizarre, unlikely circulating androgens into estrogen, and everything is working fine. But what if you're stressed? What if you're stressed like the locusts have come and eaten your crops, and you've been subsisting on 1,000 calories a day? What if you were slowly beginning to starve? What happens? Your fat deposits begin to go down. You begin to get depleted of fat. You're starving. And what happens is after a while, you have too few active fat cells to do that testosterone to estrogen conversion. And at that point, you are up the creek for two reasons. First off, you're putting less estrogen into the bloodstream. That's not that much of a big deal. It's a tiny amount. But the biggest consequence is you're now not breaking down that testosterone. Its levels build up and mess up things at the brain, pituitary, all of that. So that's this weird, from out of left field mechanism that's also relevant, this oddity of females making a certain amount of male sex hormones, and when you don't have much fat cells going there for you because of starvation, you don't do that conversion. So that's a major reason why starvation can shut down ovulation. That's also a major reason why voluntary starvation can do the same. Anorexia nervosa, one of its characteristics is that you shut down ovulation very early on. It's the fat depletion. That's also the reason why some women who do tons and tons of exercise will stop ovulating as well. Again, the fat deposit's going down. And this has actually been widely studied, the ratio of fat to muscle, the amount of fat stores, the readiness with which that conversion is going on. This has been studied in all sorts of cases. For example, in kids, prepubescent kids, most often studied in terms of girls who are very, very intense athletes, typically gymnasts, ballet dancers, the ones who are doing 6 hours a day. And what you will see is a very significant delay with the onset of puberty. And this was even shown a few years ago, a study of gymnasts from the Romanian Olympic gymnastics team. And those are those like 15-year-olds who weigh 60 pounds and are getting the gold medals. What was the average age at which these kids started menstruating? Approximately 19. Western average 12 and a half years. This is a huge effect in terms of delaying the onset of puberty. Once you've hit puberty, women who do tons of exercise, for example, runners, on the average, if you were running about 50 miles a week, that's typically when the fat deposits are getting below that threshold and you begin to have ovulatory problems. Now, I could be telling you the same exact story with males. Men who run that average of 45, 50 miles a week, typically there's a little bit of testicular atrophy, sperm count goes down. Okay, you were sitting there saying, wait a second, I thought exercise was good for you. Exercise is good for you. In fact, a lot of exercise is very good for you. That doesn't mean, though, that an insane amount of exercise is insanely good for you. At some point, you pass a point of optimal function. You pass a point of homeostatic balance, and too much of a good thing could be just as bad as too little. This winds up being very, very relevant. One of our themes again and again is optimal ranges, homeostatic balance. Okay, so what goes on at that point? What happens there is all sorts of problems with trying to make sense of this effect, trying to make sense of why the body is set up for responding to extreme athleticism. And what you've got is a theme we've had running through here. This is not typical. This is not typical for humans. Okay, how to get a sense of it. Sit down some hunter-gatherer from the Kalahari Desert and explain to them, you know, back where I come from, we have so much food and so much free time that sometimes we'll just go run 26 miles for the sheer pleasure of it. And they're going to say, are you out of your mind? This is stressful. I mean, throughout hominid history, if you're running 26 miles in a day, you are either very intent on eating somebody or somebody's intent on eating you. This is not normal hominid behavior. So again, we see the possibility of passing a point of homeostatic balance, a homeostatic ideal. Now, as I mentioned a few minutes ago, a very interesting hormone comes into play here, prolactin. Prolactin, secreted during stress, and it turns out prolactin works, among other ways, by decreasing pituitary sensitivity to LHRH. It helps block the release of progesterone, all sorts of things like that. And as promised, prolactin is not merely a hormone released during stress. It does all sorts of other things. One interesting circumstance is if you have nipple stimulation, there's this neural loop going up to the brain and the hypothalamus, and you know that whole pattern, and out comes prolactin. Nursing causes prolactin release. And given all the things I just told you, prolactin release should be working as a contraceptive. Nursing is a contraceptive. That's why that works so well. Oh, you are sitting there saying, what does he know? He doesn't even have ovaries. Everybody knows nursing doesn't work very well. Nursing works wonderfully at being a contraceptive. The World Health Organization estimates there are more pregnancies prevented each year by nursing than by all other contraceptives put together. All you need to do is nurse the correct way, which I'm going to show you now. Aren't you folks who went for the audio version regretting it now? Okay, so what is human nursing like? Well, it depends. If you look at women in westernized countries, you see the following pattern. Typical pattern: you give birth, you nurse your child every couple of hours for 20 minutes or so. Typically, it begins to get lesser amounts of time. In the West, in the United States, women on the average nurse for 6 months. So what are you doing if every few hours or so you're nursing for 20 minutes? You begin to nurse, up go prolactin levels. You stop nursing, down they go. 2 hours later, up go prolactin levels, down they go. You get this scalloping pattern of prolactin up and down. That's not what humans and other primates normally do with nursing, and thus with their prolactin levels. And to get a sense of that, this was first really studied in a bunch of hunter-gatherers, the folks living in the Kalahari Desert, the Kung Bushmen living in the Kalahari Desert, and they have a very interesting reproductive pattern, which is they have tons of sex, they don't use contraceptives, and despite all of that, women get pregnant about once every 4 years. What is causing that pattern to emerge? Now, the answer was very easy back then when people looked at hunter-gatherers and said, well, what's hunter-gatherer lifestyle like? Short, nasty, and brutish. They're all malnourished. They're all depleted of sufficient fat to ovulate. When people actually go and study hunter-gatherers, it becomes clear agriculture was one of the all-time stupid moves inventing that. Hunter-gatherers live very comfortably. As termed, they were the original affluent society. Folks like these are working 3-4 hours a day to get their day's calories. They are not short, nasty, brutish, and starving and depleted of estrogen. So what's actually going on there? What's going on was discovered a number of years ago by two anthropologists, Melvin Connor and Carol Worthman, and what they did was they noticed the prolactin pattern, the nursing pattern in women hunter-gatherers. And what you see there is something very different from in the West. Here's what happens. You give birth and you nurse your child for 30 seconds. And 20 minutes later, you nurse your child for 30 seconds. And 20 minutes after that, and you do that around the clock for the next 3 years. You carry your child on a hip sling and nursing every 20 minutes or so. You nurse throughout the night so that the mother hardly even wakes up. The baby just sort of crawls over and does some nursing. Mom continues to sleep. Oh, of course, Connor and Worthman are there up at night with their infrared goggles and stopwatches, but everybody else is undisturbed. And 3 years into it or so, your child is still nursing every 20 minutes or so. They come running in from the Little League game to nurse for a little bit. And when you have a nursing pattern like that, the first time you nurse for those 30 seconds or so, up go prolactin levels, and they're going to stay up for the next 3 or 4 years. That's the typical human and non-human primate pattern of nursing. And you do it that way, and you get this huge square wave nonstop of prolactin, you're not going to ovulate. That's what explains that delayed pattern of fertility. Think about that a second. Okay, what's the life history like for one of these women? Here's what you do. You hit puberty maybe when you're about 14 or so, typically a little bit later than in the West. And a year later, you're pregnant. And from what we just saw, 4 years later, you begin to ovulate again. Couple of cycles, you get pregnant again. 4 years later, couple of cycles. Eventually, you hit menopause, and you suddenly realize, my God, over the lifespan of these women, they're having maybe a dozen periods. And you look at women in the West and you get 300 or 400, and what you realize is the pattern of nursing in the West produces far more, like tenfold at least, more periods sloughing off of cells from the uterus than is the typical human and primate pattern. And there's lots of reasons to believe that increases the likelihood of a number of diseases in women, one, for example, being endometriosis. Okay, so that's another realm of vulnerability. Pushing on, another domain where stress becomes relevant, at least with all sorts of theorizing, is the realm of high-tech reproduction, in vitro fertilization. And anyone who has ever gone through this or been near someone who goes through this is enormously stressful. Your entire lifestyle is dislocated. You are getting filled up with synthetic hormones that wreak havoc with mood, with metabolism. Sex becomes a timed chore. It's a very very high failure rate. You spend a fortune on it, usually not reimbursed by insurance. It's enormously stressful. And thus, there's been an obvious conclusion to reach, which is stress makes IVF, in vitro fertilization, less likely to actually work. Seems perfectly obvious. At this point, the evidence for it is mixed. It's so-so. It's not one of the more vulnerable realms of female reproduction when it comes to stress. And what I can absolutely tell you is the worst consequence of recognizing that stress might have something to do with success rates with high-tech reproductive approaches. The worst thing you can do is to have your physician, have your family, have your friends sit you down and say, oh, did you know that stress can disrupt reproduction in IVF? So just don't get stressed as you go through all of this. This is like ridiculous and one of the worst realms of applying the knowledge coming out of this whole subject. One additional realm now in terms of stress and reproduction, which is you've gotten the fertilization to occur, you've got a pregnancy to start, and something that is classically vulnerable here is the possibility of chronic stress causing a miscarriage, a spontaneous abortion. Now, the possibilities of this, the mere fact that stress can cause a miscarriage, that is run through all sorts of classic literature, all sorts of novels where key points of stress, of betrayal, of infidelities causes grief and stress and miscarriage. And I could cite the names of those books if I had ever actually read any of them. But this is a theme that goes through these, and it fits. It works. In lots of non-human species, what you will see is lots of stress causes spontaneous miscarriages. In some species, it takes the form of harassment. And often a pattern that you see is a high-ranking female in some social species that's hierarchical. A high-ranking female can harass, can stress fertile, pregnant subordinates to the point where they miscarry. There's even some very elegant versions of this where the stress of the smell, the odor, the pheromonal signal of a big, scary, dominant female can cause miscarriage. So what's going on with humans with that? What's happening there? It can happen. It can happen, but the evidence for it is not very good. It's not good because it relies on what is dreaded in these fields of epidemiology, what's called retrospective data. Something bad happens to someone in terms of a disease, and it may be a disease where people think about stress, so they sit you down while the something bad is happening big time, and they say, have you been stressed recently? And it's like guaranteed that someone is then going to say, yes, I've been stressed. When people are in the middle of some awful circumstance, they preferentially remember bad things in their past, and suddenly you come up with all sorts of bits of stressful history there. And you can even show this in studies. This was one classic study where I don't know how they pulled this one off, and you couldn't do this with human subject rules anymore, but people were given some sort of drug that made them have like this horrible stomach ache for weeks afterward. As you can see, this really is not a modern type experiment, but what happens at that point is the person goes to their doctor, and the doctor is in on the experiment and says to them, oh, this is terrible, you have an ulcer. They don't have an ulcer, they've just taken this medication, this experimental drug that's making them feel sick, and they don't know they took it. This crazy study, but the doctor at this point says, oh, you have an ulcer. So has anything stressful been going on in your life? And because everyone knows stress and ulcers, we saw a few lectures ago how it's more complicated than that. Stress and ulcers, people are suddenly coming up with all sorts of stressors that could explain why they've gotten sick. Same thing in all sorts of retrospective studies where you ask somebody at the time they've gotten bad medical news, so anything stressful going on recently, and people come up with numbers of those events like crazy. So it's very hard to trust studies like that. So what you do then is, in some cases, prospective studies, when you look at pregnant women and the stress increase their likelihood of miscarriage, that definitely can occur. One thing that you see, though, is it's a slowly emerging process. So the bias that one would have is, the morning of my miscarriage, I had some horribly stressful event. That probably had nothing to do with it if it is stress-related. It's stressors stretching out quite a few days. So when that does happen, what are the mechanisms for it? And we go straight back to the earlier lectures. You're running for your life. You're shutting off all the optimistic long-term processes. You are delivering blood to wherever it's needed, those exercising thighs, and you're delivering blood at lower rates to parts of the body that are not essential. We saw earlier on one possible consequence of this is by delivering less blood to your gastrointestinal system. In some ways, you set yourself up for an ulcer more readily or less able to repair it. Down in this realm, women, female mammals who are chronically severely stressed when they're pregnant, they decrease blood flow to the fetus. And that's triggered by the sympathetic nervous system. And you do enough of that and you increase the likelihood that you are going to lose the pregnancy. Okay, so that is the realm of what stress has to do with fertilization, ovulation, thickening your uterine walls, maintaining a pregnancy, high-tech in vitro fertilization. One additional area comes in having to do with another feature of sex, one that has long puzzled all sorts of scientists ranging from evolutionary biologists to psychoneuroimmunoendocrinologists, which is, sex feels good. Lots of times, we take great pleasure from sex. We have a drive towards sexual behavior. Pulling out Freud for the first time, a Freudian term, there's libido, sex drive. And another thing that occurs with chronic stress in both males and females, your libido goes down. You have less interest in sex. What is that one about? You are secreting all sorts of the stress hormones, as we know, and two general realms where things happen. You've got all sorts of interesting parts of your body that are sensitive to certain types of tactile stimulation and more sensitive when you have high levels of certain when you have high levels of certain reproductive related hormones in your bloodstream. It makes all sorts of tactile receptors in your genitals and your earlobes and who knows where else more sensitive, more responsive to tactile information. Down go those reproductive hormones, and sensitivity in those areas are blunted, and things don't feel as good. One additional piece, a brain chemical called dopamine. Dopamine has everything to do with pleasure. Cocaine works on the dopamine system in the brain to release dopamine, and you feel pleasure or the anticipation of pleasure more frequently. And what you wind up seeing then is a very simple fact. Sex, good sex, tends to release dopamine. Nobody has studied this a whole lot in humans, but hamsters, when they have good sex, release lots of dopamine. Lots of dopamine. So what happens with chronic stress? You don't have as much dopamine in that pathway. It tends to get depleted, and suddenly sex is less pleasurable. So here we have a broad overview of what goes wrong with the system. And remember that piece about dopamine, because that's critical. That is going to come back to haunt us big time when we see what chronic stress has to do with the lack of pleasure of a major clinical depression.
Lecture 9. Stress and Male Reproduction.
Well, we're here again, and it's time for more fun with dysfunctional reproductive systems. And now we move over to the world of males. What were the themes that came through the previous lecture? The complexity, the cost of the female reproductive axis, and the mere fact that major chronic stress, and this is no time for it. As we'll see, some of the same exact themes with males. And we saw one example of it already in the previous lecture, which was that business about women who do tons of athletics, women who are starving, that business about fat stores dropping down, and mentioning that business in passing. Males don't do that androgen to estrogen conversion we were talking about. But nonetheless, when males do tons of athletics, as mentioned, on the average male runners who run 45, 50 miles a week, for other mechanisms that we will hear about, sperm count tends to go down, number of viable sperm as well, testicular size, this theme that we've already recognized. Now, switching over to making sense of the male reproductive system and the effects of stress, it's not just pertinent to runners. It's not just pertinent to extreme exercise. It comes up in all sorts of realms. And it's the same exact lesson once again. You can do this one readily and tell the themes short term, you're running for your life, make your sperm some other time, do it chronically, and you are going to pay a price. Now, what it all revolves around is testosterone. Testosterone, this key hormone, this key steroidal hormone that comes out of the testes. Yes, you know the drill by now in terms of an axis, the hypothalamus to pituitary to testes, but the place to start is emphasizing that when you look at this version in males, it's just a lot simpler than in females. To wit, the male brain is just a whole lot simpler than the female brain, at least when it comes to reproductive physiology. Why is this the case? It's because female brains and the female reproductive axis has to do something much fancier than in the male. They have to have cyclic release. They have to have things churning along, and right around day 14, there's massive changes in the levels of this and that takes some very fancy wiring. The male brain, in contrast, all it needs to do is just dribble out a certain amount of testosterone on a regular basis. It's much more of a flat level. And this is brought about predominantly during fetal life when fetal brains are either intentionally or inadvertently poisoned with androgens. You wind up with a simpler male brain, one where testosterone release is fairly constant over time. Of course, it's not absolutely constant throughout. It responds to experience. You get some guy who's facing off against his worst rival on the whole planet, and he crushes him, defeats him at Chutes and Ladders, and he is going to have this atavistic surge of testosterone. Will make him glow like a baboon on the savannah with sharp canines. Yes, it responds to that, but for the most part, males are these lumpen endocrine creatures. You get a stimulus like that, you get a 3, 4, 5-fold difference in testosterone levels, and you look at females and there's these massive fluctuations again, so the female reproductive system is much more complex than in the male. Nonetheless, amid that simplicity, the male reproductive system is vulnerable to is vulnerable to stress in some of the same exact ways. And as you would guess already, with the onset of stress, down go testosterone levels. Same theme as with the reproductive hormones in females like estrogen. Your testes do not know what they are doing. Back to the earlier lectures, they are not autonomous glands, but instead it's that same business axis starting in the brain to the pituitary to the testes. So which hormones are relevant? And weirdly, it's almost the exact same hormones as in the female. From the pituitary out comes LH and FSH, follicle-stimulating hormone and luteinizing hormone. And since men don't have follicles, you're not stimulating follicles with FSH, you're stimulating the production of sperm. LH, luteinizing hormone, is predominantly responsible for stimulating testosterone production. Same exact deal as in females. The pituitary doesn't know what it's doing either. So back up in the brain, same hormone again, LHRH, luteinizing hormone, releasing hormone. We've got our basic axis here. So the simplified male brain in its sort of constant state of hormone release does its LHRH business, LH and FSH from the pituitary, out goes testosterone. Now, the basic theme that runs throughout all of this is, you guessed it, with the onset of stress, down go testosterone levels. You take some guy and you put him through surgery, he's anesthetized, you slice into his belly with a scalpel, and within 10 minutes or so, testosterone levels are going down. You take first-year male medical students during their final exams and down go testosterone levels, which you may want to take as a cautionary point if any of you males out there are pre-meds. It doesn't come cheap. Another realm in which testosterone goes down takes a male baboon who sits there way up on top of the hierarchy and do some vicious manipulative things so the guy drops in the hierarchy. Down go testosterone levels built around the stress of that circumstance. Now here's a stressor which, thank God, I have no personal experience with whatsoever, but apparently it's not fun to be in the Marines. Apparently it's kind of a drag, in fact, especially during military training. And this was this classic study, 1970, New England Journal of Medicine, looking at military officers' training during this first couple of months. And now, in addition to all the other indignities, these guys had to pee into these little Dixie cups where the psychiatrist would then take over and the endocrine people would analyze the hormone levels. And back comes the finding that you look at guys during the first couple of months in the Marines and they've got the circulating testosterone levels of newborn babies. And you may want to keep that in mind the next time you're in a bar and there's some leatherneck bragging about his androgen levels, and just get him up to date on modern endocrinology, and maybe he'll even buy you a drink. Probably not, no need to mention my name. But what we see here are all these circumstances where testosterone levels go down. So, of course, as usual, we have to ask the question, what are the mechanisms? Which hormones released during stress mess with this testicular system? And it's some of the exact same culprits as with the female system. Glucocorticoids, working at the level of the brain to decrease the release of that luteinizing hormone releasing hormone. Glucocorticoids working down at the testes to make those testes less sensitive to whatever pituitary signals are coming out. That same theme again, less messenger coming out of the brain and the pituitary, less sensitivity in the pituitary and testes to these signals. Interesting additional hormone that becomes relevant, and it's one that's now been mentioned a few times in the last lecture, for example, beta-endorphin. Beta-endorphin, another hormone that's released during stress, and we saw that beta-endorphin has some anti-reproductive effects in females, virtually the same thing in males. And around this point, you begin to try to put some pieces together. Okay, beta-endorphin, hormone we haven't mentioned much yet, a hormone that is going to dominate the coming lecture about stress and pain, because beta-endorphin is your brain's equivalent, your brain's chemical equivalent of morphine. Morphine, heroin, pain-blocking drugs like opiates, beta-endorphin, endogenous morphine. And of course, there's a whole world of people out there who abuse opioids like that. So you suddenly come up with this wondering question here. Do people who are morphine, heroin, opium addicts, do they have problems with their reproductive systems? Absolutely. That is absolutely the case in males and females. Okay, so we have lots of these steps going on here. Doing in sensitivity to the hormone, doing in the release of the relevant hormones, and the net result is less testosterone. So at this point, you have to ask a very critical question. And this is one that goes through all the physiology. There's a tendency to be very impressed with the change in the levels of some hormone or some brain chemical or activating of some gene or suppressing of some gene or doing something rather to some enzyme. And people consume entire careers being excited about the minutia of this and how. And somewhere along the way, you have to ask this very out-of-date sort of question that runs through physiology, which is, what are the consequences of this? What are the physiological consequences? And thus, we must ask the question here, what are the consequences of testosterone levels going down during stress? And you can imagine all sorts of things. Males have all sorts of problems, and aggression goes down, and all sorts of things that happen at that point, not working very well. And when you look at it, there in fact is a very surprising finding, which is there are no consequences of testosterone levels going down during stress. And just to prove it, my voice just cracked in a peripubescent way. There's no consequences. testosterone turns out to be this vastly overrated hormone. It's virtually superfluous. You need like basically a thimbleful of the stuff and a couple of sperm to be in business. Testosterone really is not that interesting. You've got to knock down levels of it enormously in order to impair fertility. What does stress do? It knocks down levels, but typically nowhere near in the range to mess up testosterone and fertility. So the consequences there are pretty clear. There's not much in the way of consequences. So where are the consequences? And it turns out the problems during stress are not that testosterone levels go down. The problem is that penises go down. Am I allowed to talk about penises in Fairfax County? Okay, I just got the thumbs up from the team of teaching company lawyers standing just away from this fine dark wood set. And we're all set now to finally, so many lectures in this course, to talk about erections. How do erections work? Turns out, in a very complicated way. No surprise. Very complicated way. The thing that you have to do for starters is a spinal cord. And we heard earlier on, the spinal cord carries information from the brain signaling to voluntary muscles, and that's that boring world of the voluntary nervous system, doing the foxtrot, etc. That's not the part that's interesting, and you can guess immediately what becomes relevant: the autonomic nervous system. All that stuff that we normally can't consciously control, goose flesh, blushing, all of that, this is where erections come in. Now, we had a theme in these earlier lectures when first learning about this autonomic nervous system, which is those two halves: sympathetic nervous system, parasympathetic, sympathetic arousal, emergency, stress, adrenaline, parasympathetic, calm, vegetative function. And what we saw in these earlier lectures are the extent to which these two systems work in opposition. You want to activate the cardiovascular stress response, increasing blood pressure, increasing heart rate, all that sort of thing. And we saw a great example of the autonomic nervous system working in opposition. What do? You activate the sympathetic nervous system and you inhibit the parasympathetic. And in fact, when you look at the systems there in more details, activating the sympathetic sends actively a pathway, a collateral projection that inhibits the parasympathetic. When you activate the parasympathetic, there's a collateral that comes off that inhibits the sympathetic nervous. What do you see here? This is a mechanism to guarantee that you never inadvertently put your foot on the gas and the brake at the same time. So opposition there, heart function. Same thing, but with a very different twist. Same thing that we saw earlier in terms of gastrointestinal tract. What we saw was with the onset of stress, with the onset of activation of the sympathetic nervous system, you decrease activity in your gastrointestinal system. That whole business, your stomach contracts less peristaltic directional contraction in your small intestines. We got that small footnote about the increased activation down there in the large intestines and getting rid of the dead weight. But the main point there is, in this case, the sympathetic nervous system pulls off its stress response by decreasing activity in the gastrointestinal system. Parasympathetic does exactly this theme again and again of sympathetic and parasympathetic working in opposition. When you get to the world of erections, things suddenly work differently. This is the first time where there's not a clear opposition, but instead this amazing choreography that goes on. So here's the deal. In male primates the world over, you need to activate the parasympathetic nervous system in order to get an erection. And very broadly, erections come in two different flavors. There's what's called a hemodynamic erection. And what goes on there is you get an erect penis by way of increased blood flow. More blood goes into the penis, you decrease the blood flow out of there, and you got yourself an erect penis. In the other cases, it's a muscular erection. There's this muscle called the levator ani muscle. And what it does is when it gets stimulated by the parasympathetic nervous system, it contracts and up goes the penis, like during, pulling up a sail or some such thing. Humans have the hemodynamic, rodents have the muscular. Muscular happens faster, lasts shorter, humans last longer, take your pick. But nonetheless, in both cases, it's driven by the parasympathetic nervous system. So how do erections and then ejaculation work? Here's what you got. parasympathetic activity. So you've managed to turn on the parasympathetic nervous system, you are calm and vegetative, and you got yourself your erection now. So what happens next? Maybe something having to do with the social context that brought about the erection in the first place. Maybe for some obscure, inexplicable reason, you begin to feel a little bit less calm and vegetative. Maybe your heart's beginning to beat faster. Maybe you're starting to breathe faster. Maybe you're beginning to exert some muscular exercise activity thing. What are you doing? You are slowly turning on the sympathetic nervous system. More time goes by, more activation of it, more heart rate, more cardiovascular, and eventually you are blasting with your cardiovascular tone. Your heart's beating fast, blood pressure, you're sweating, your toes are curling, you're exercising like crazy. Eventually reach this point where your whole body is screamingly sympathetic, except for this one lone outpost where you're desperately holding on to parasympathetic tone as long as possible. Finally, you can't take it anymore. You turn off the parasympathetic, you turn on the sympathetic, and you ejaculate. Okay, so that's how erections work. That's how erections work. And what happens during stress? What happens during stress? It's perfectly obvious. You're not feeling all that calm and vegetative. You can't turn on the parasympathetic nervous system. And suddenly, you got this problem there of stress-induced impotency. But there's a second problem that might come in. Suppose you manage to pull things off and you've got yourself this erection and things are starting just fine, and suddenly you think, oh my God, the dollar exchange rate for the euro, and something happens, and suddenly you get all anxious and you accelerate that transition from the parasympathetic to the sympathetic. What happens then is premature ejaculation. So you've got this whole world of vulnerability, and this is a world of extraordinary vulnerability. Erectile dysfunction, either you can't get the erection or you have this problem with premature ejaculation. It is incredibly easy for this to occur. Current estimates are 60% of the doctor's visits in this country are due to not organic cases of impotency, but to psychogenic, stress-related. Now, mind you, a number like that you got to take with a certain degree of skepticism. Anytime you say stuff like psychogenic instead of organic, at some point or other, all cases of erectile dysfunction were psychogenic in nature. What does that mean? Nobody had discovered an organic explanation yet, and as one gets more and more organic explanations, the incidence of psychogenic go down. Given these caveats, nonetheless, this is a system that is spectacularly vulnerable to stress effects. So now we have this challenge, which is how to tell the difference between an organic case of erectile dysfunction or a psychogenic case. And here's where you finally get something useful out of this damn course where you should take notes. Here's where we see how you make this differential diagnosis. Okay, some guy comes in, and he's complaining about how he hasn't been able to have an erection during sex in the last 6 months. And you think, well, is this organic in basis? Maybe the guy has a pituitary tumor or something wrong with his spinal autonomic projection, some such thing. Or is it psychogenic? You're trying to distinguish between the two. And here's what you do. You take advantage of a totally weird thing that male primates do, at least as weird as that business about female primates secreting a certain amount of male sex hormones. Now this weird thing that male primates do, including human males, which is when they go into REM sleep, rapid eye movement sleep, they get erections. I have no idea why. I've talked to Earth's experts, penis experts, and none of them have a good explanation. Nonetheless, males get REM sleep erections. Nothing you can do about it. So here you are, you've got this guy where you can't tell if he has a case of psychogenic or organic erectile dysfunction. Here's what you do. You give him this handy-dandy little penile pressure cuff transducer thingy, which he puts down on the base of his penis at night just before he goes to sleep, and he wires it up and satellite relays and 24-hour operators in Bangalore. And the next morning, you got your answer, which is, if this guy hasn't had an erection in sex in the last 6 months, yet 30 seconds into his first REM stage, this guy doesn't have a brain tumor, it is psychogenic. That's how you distinguish between the two. Do you still get the nocturnal erections? Do you still get the erections during REM sleep? Show that pattern, and it is psychogenic in nature. So that's very easy to differentiate between the two. Actually, it's not so easy to differentiate the two if you really think about it, because, you got this electronic device on your penis there, and it's beeping and wires, and you're so sure it's going to electrocute you during the night that's a stressor in and of itself. Here is what you do instead. And this is actually what is done most commonly in sexual dysfunction clinics, a wonderfully elegant piece of diagnostic approach. Here's what you do instead. You take a string of postage stamps and you lick them at one end and you wrap them around the guy's penis. He goes to sleep, and the next morning, if the stamps have been torn loose at one end, the guy had an erection during the night. Can you believe how elegant that is? Forget, electronic devices and cutting-edge tech. All you need is a bunch of postage stamps. It's wonderful, like $5, and you get a medical diagnosis. It's great. And, of course, insurance isn't going to pay for it, but someday that will change in this country. So what you see here is a domain of great vulnerability to stress effects in terms of testosterone levels going down. Not such a big deal, as we saw in terms of consequence. Erectile dysfunction in terms of problems having an erection. Once you have it, accelerated transition from parasympathetic to sympathetic, premature ejaculation, that problem there. And this challenge of differentiating between when erectile dysfunction is due to some sort of organic problem, and when it is due instead to some sort of psychogenic problem. And the cutting edge thing that makes one like me proud to be a biomedical researcher, the role of postage stamps in modern medicine. So all of this is great. We have a great deal of insight now into how the male body falls apart during stress. And as we saw, probably the most influential piece of that is that business about the sympathetic nervous system as activated during stress, making it very hard to have an erection. And most of the time when you see problems with this, again, they appear to be psychogenic in nature. So this is a universal. This is how everything works, except there's one interesting case where you get exceptions, which is, we've got this logic by now, running for your life, the predator coming after you, you got better things to do than, make sperm, you're in the middle of some socially stressful period. But there's one area where it actually doesn't make sense to inhibit the male testicular system. Suppose you are some male moose or something at the top of the dominance hierarchy. You've just fought your way to the top, and it is mating season, and there are males challenging you left and right, and lots of fighting and butting of heads, and very stressful, very stressful. What a disaster it would be if you have this whole period of fighting like mad, being stressed like mad, in order to come out in dominant position and get the chance to mate, and you can't get the chance to mate because your whole testicular system is suppressed there. In cases like that, there are mechanisms by which the reproductive system in males are protected from that particular type of stress. Nonetheless, in circumstance after circumstance, what we see is stress of all sorts of forms, physical or psychogenic, shutting down the reproductive system. And again, probably the most important step in there is hyperactivation of the sympathetic nervous system, and you're not going to get an erection. So this appears to be universal until you suddenly find one species where it doesn't quite work this way. And it is time, finally, so many lectures in this course, it is time that we finally talked about hyenas. Okay. Hyenas. What's the deal with hyenas? Spotted hyenas, have horrible public relations problems because of how all of us think about hyenas. To the extent that any of us think about hyenas, and I assume most of us do, hyenas. What's the scenario? It's one of those Marlon Perkins Wild Kingdom type scenes there where it's dawn on the savannah. And you open up and there's some carcass of something or other and a whole bunch of lions eating on it, and you get close-ups of them, drooling in excitement, and it is wonderful. And then you suddenly see right on the edge of those lions there, you see them, those skeevy hyenas, those scavengers looking for a chance to run in there and get a scrap of meat. Hyenas are scavengers. They're not real hunters, and all of us root for hunters instead of scavengers, which is pretty odd since what most of us are scavengers as we go up and down the meat aisle in the supermarket. Not a lot of us have taken down our kills with our canines. Nonetheless, we love those lions, and there are those skeevy hyenas lurking around on the edge looking for a little piece of something dead where they had nothing to do with bringing it down. This turns out to be nonsense. This turns out to be this horrible bit of, urban legend going against our admiration for the hyenas. It turns out hyenas are great hunters. They're extremely organized hunters with high success rates. And the reason why people really didn't appreciate it for a long time was looking at lions through rose-colored glasses and the fact that hyenas are nocturnal predators. So you have these hyenas, and they've taken down a kill, and it turns out lions are not very good at hunting. They're big, they're conspicuous, they're relatively slow. They have a much lower success rate than you see in hyenas. What lions are really good at is booting hyenas off of their kill. So here you have the hyenas who've brought down the kill, and the lions come in and boot them off, the lions who are now the scavengers, and in comes Marlin Perkins with the film crew, and no wonder the hyenas are looking all skeevy out on the edge of things. They're the ones who were up all night hunting, and who's having the steaks now? So hopefully what this has done is pulled out a high degree of sympathy towards the poor maligned hyena, which is a good thing now because what I'm about to tell you may wipe out that sympathy because hyenas are really weird. Hyenas break all the rules of what boys and girls are supposed to be about. For a simple reason, not so simple, but for a very clear reason, hyenas have a sex reversal dominant system. What do I mean by this? Among hyenas, females have more muscle than males. Females tend to be more aggressive. Amazingly, females have higher levels of one type of androgen, one type of male sex hormone. Females are socially dominant to males. And here's the weirdest thing. Females have genitals that look just like those in males. They have something or other gets erect there, and they have something or other that looks like a scrotum, and it's totally bizarre. And it turns out they really don't have erections in a scrotum. What they have is not a penis, but a clitoris, and they get clitoral erections, and they don't really have testes. They have these compacted fat cells that kind of look like, and it's all totally bizarre. And what it's all about is this weird androgenization of female hyenas. So you can't even tell, what gender one of them is. As I think I've mentioned, I do research some of the time on baboons in Africa. And over the years, I've shared camp with a scientist from Berkeley who is the world's expert on hyena clitorises. Centuries will go by, and it will be impossible to talk about the subject without mentioning this man's name. He is as wise on the subject as you can get. And you would see these cases there in camp where he's darted and anesthetized some hyena, and he drags it into camp and looks down in there, and he's got his binoculars, and it takes him a long time to say, well, I think this one's a boy or this one's a girl. They've got this bizarre sex reversal system that involves androgenization of the genitals in the female. Weird, utterly weird, except it turns out it makes sense. Which is, among lots of social carnivores out there, you give birth to a large number of kids, a litter of a dozen lion cubs, and what you've got then is this vicious competition for food where the majority of those cubs don't make it to age 1. For a bunch of gynecological reasons, hyenas only have a couple of pups, a pair of pups, and you get that low of a number, and you are suddenly under big evolutionary pressure to get those kids to survive. And suddenly, some hyena, way back when, got a mutation, probably in the ovaries, where they now start pumping out lots of those androgens, not the piddly levels we heard about in the previous lecture. They pump out lots of these androgens, and suddenly you've got a female who is big and snarly and muscular and aggressive, and suddenly she is the one who gets to feed her kids. You've got a bunch of hyenas who take down a kill, a bunch of male hyenas, and in come the females and boot them off, and the kids get to eat first, and you do that food access sort of hierarchy, and your kids do not starve to death. So here's this dominance reversal system. So where do the weirdo genitals and stress come in? As follows. In most species, among male primates, for example, erections are about social dominance. And you get some high-ranking male who expresses and he's waving his erection and penis around. Among hyenas, you get just the opposite, which is an erection is a sign of social subordination. You have some poor low-ranking male who's about to be pounded on by a female. What does he do? He gets an erection saying, please don't hurt me, I'm one of those snivelly males. You get a low-ranking female hyena. She does the same thing with her clitoral erection. And suddenly we get to the whole point of this long, pointless digression, which is amid all those species where activating the sympathetic nervous system wipes out erections. Among hyenas, the wiring has to be that the sympathetic nervous system causes erections. So what we've seen here is an example of phylogenetic variability and the wonders of nature and all of that. And I would conclude at this point that anybody listening to this has to be overwhelmed with the need to learn more about the subject. So we will stop here and give you a chance to write letters now to the teaching company demanding more and more courses about hyenas. So off you go to form those letters.
Lecture 10. Stress and your immune system.
Well, I have just been dry cleaned and I've got a new fuzzy sweater, so time for a little Jimmy Carter-esque fireside chat about our next topic, stress and the immune system. Now, if you hang out with scientists, you'll notice they have a very irritating tendency, which is they like big words, they like complicated words, they like multisyllabic words, they like them to substitute for much easier concepts. For example, there's a stress-related disease called idiopathic alopecia areata. What is it? It means you lose your hair for some mysterious reason. Idiopathic, instead of just saying, we don't know. So there's all sorts of these fancy terms, and back in those ancient days for which you feel nostalgia, words like endocrinology or neurobiology counted as those satisfyingly long words, but in recent years it hasn't been enough. And you get even longer terms, and suddenly this is this world of psychoendocrinology or behavioral socioendocrinology or neuroeconomics or, I kid you not, something called neuromarketing. And amid all of that, there's been another multisyllabic term, a brand new field, which has emerged somewhere since the 1980s. And this one will dominate this lecture. This one has some of the most syllables around. This one is called psychoneuroimmunology. And the basic premise here is what's going on in your head, what your psychological state is, has something to do with how your immune system functions, how you fight off infectious diseases. Now, the evidence that something as bizarre as what's happening in your head can influence your immune system, something like that, in fact, goes back quite a few centuries. And the first evidence for this was this wonderful study back in the 1800s, and I wish I knew who had the intuition to do this, but you take people, back when, with a rose allergy, and you get an 1800s version of an artificial rose, probably not plastic, and you wave it in front of one of these people's noses, and they suddenly start sneezing. Not because this was a real rose, but because of psychoneuroimmunology kicking in. Their immune system, their inflammatory system in this case, got tricked into starting to sneeze. Or another more recent study, another wonderful example of how this system works, and this was a study done with professional actors, and what they did was spend a day reading through a scene, practicing a scene that had some sort of horrible, catastrophic event in it. And a few days later, they spent the day reading through a scene that had some wonderful, buoyant news in it. And what do the scientists observe? Spend a day pretending that you are in the middle of some horrible, distressing, disastrous scene, and by the end of the day, your immune system is not working quite as well. Sit there and spend a day reading about some euphoric scene that you're acting your way through, and by the end of the day, your immune system is working a little bit better. Not surprisingly at all, this was carried out at UCLA, sitting there in Los Angeles, and no shortage of actors who are willing to have their immune systems futzed with, but this is the sort of informal evidence that this field, this psychoneuroimmunology, is for real. So how does this work? And especially, how does stress impact the system? Now, to appreciate this, we have to have a little bit of an overview of how the immune system works. And I know in this day and age, it's very important to do something confessional, so I will confess here, I am terrified of the immune system. I have felt that way since kindergarten because it is unbelievably complicated. So if you don't panic, I will try not to, as well as we go over the basics of the immune system. What the immune system does is protect you from pathogens, invasive thingies that don't belong in your body that can make you sick. Most broadly, bacteria and viruses. Viruses that are especially clever, what they can do is insert into your DNA, insert their viral DNA, and use that to take over your cells for their own nefarious purposes. The immune system's job is to constantly be on the lookout for bacteria and viruses, and when they spot them, to quick mount an attack. The immune system is also built around attacking cancerous cells, the starts of tumors, but the main thing they're about is going after invasive pathogens. And this is done in wildly complicated ways. What you see is, for one thing, all sorts of subtypes of immune cells that activate the system and suppress the system and activate the suppressors and suppress the activator. They come with all sorts of names. There's even like tough guy immune cells, like called natural killer cells. This whole array of different types of immune cells. Broadly, there's two categories of immune cells, white blood cells, lymphocytes. Broadly, there's two categories having to do with two different functions, two different origins. Now, the immune system, new cells are made in various places. New immune cells, they're made in your bone marrow. Some are made in your thymus gland. Others are made in your spleen, your lymph nodes. So broadly, there are these two classes, T cells and B cells. T cells originate in the thymus. B cells mature in the bone marrow. Very simplified version here for our purposes. Now, what T cells and B cells do are very different things. What does a B cell do? It is constantly surveying your body to look for those pathogens. And what happens when it encounters one of them? It has this brilliant capacity to recognize what doesn't belong there. And when encountering one of these things, it starts to make antibodies that are specific to this pathogen, antibodies that will recognize this pathogen. And what those antibodies do is help to activate the T cell immune response, which is a whole bunch of these T cells to home in on whatever this pathogen is and blow it to smithereens. Now, naturally, pathogens aren't just sitting there passively getting blown in by the immune system, and just as the immune system evolved to be fancier, pathogens evolved to have fancier defenses against the fancy immune system, what might be termed coevolution. So you see all sorts of vicious tricks. There's this bacteria, this tropical one called trypanosomes, a parasite, and what trypanosomes are able to do is they keep switching proteins on their surface, the sort of proteins that B cells would home in on to make antibodies. So you've got some trypanosome protein on the surface there. B cells spot it, doesn't belong there, start making antibodies, and just in time to attack those trypanosomes, the trypanosomes have put in new different proteins, and the immune system can't find it. Very complicated coevolutionary battles. So what you find are the two basic features of what's called the adaptive immune system, the fancy stuff, T cells and B cells. Then there is this ancient part of the immune system, which refers to innate immunity. This is ancient, like bits and pieces of innate immunity have been found in insects of that sort. What B cells and T cells are about is specifying, going after some specific pathogen. What innate immunity is about, innate immunity is all about inflammation. It just kicks in any sort of infection, any sort of injury, and you just kick into action there with your innate immunity. And this is not 2 weeks later making your antibodies. This is, you get a cut and you get inflammation there, being all set to attack any bugs that get in there through your injury. So we've got the fancy top of the line adaptive immunity, T cells and B cells, and then we've got the simplistic first ones in there, inflammatory response, innate immunity. So what does stress do superimposed on this? The first thing that happens, which was brought up in the very first lecture, is with the onset of stress, you activate the immune system. Particularly, you begin to activate that adaptive immunity. How do you do this? Not surprisingly, you take advantage of the fastest part of your immune system, the adaptive stress response, and you take advantage of one of the fastest features of the stress response, the sympathetic nervous system. In addition, glucocorticoids in the very early phase of the stress response help to activate the immune system. And by now we see the perfect logic of it. You've had a tense meeting, your boss has ripped your innards open, dragging in the dust, blah, blah, and this is a good time to activate the immune system. This is what happens. Naturally, it is enormously complicated. And part of what you see is not only sympathetic nervous system and glucocorticoids activating the immune system, glucocorticoids also swoop in and do things like kill some of your old immune cells. So you sculpt out your immune response so that the ones that are on the scene are really critical. Some really nice work by Firdos Darbar at Stanford University showing another thing that happens during that time is the immune response takes circulating immune cells and rushes them over to wherever the injury is, what he has termed moving the soldiers from the barracks to the battlefront as quickly as possible. All of this highly, highly adaptive. So what happens, of course, with the problem of stress when it goes wrong? Now, the first thing that happens has to do with that short-term stress response and its short-term effects on immunity. What you begin to see is sometimes an increased risk of autoimmune diseases. Now, what is an autoimmune disease? As already noted, what's going on is your immune system is going throughout your body and looking for things that shouldn't be there. Pathogens, bacteria, viruses, all of that. Thus, what the immune system is brilliant at is telling the difference between, here's the jargon, self and non-self. Self, it belongs there. Non-self, you activate an immune attack, and it's going around and it says, hemoglobin, part of us, good thing. Virus, bad thing. Nose, good thing. And what happens is it then attacks the stuff that isn't supposed to be there. What an autoimmune disease is about is your immune system screws up and decides that a part of you that absolutely is normal and should be there, in fact, is some invasive pathogen and attacks that part of your body. And there's a whole array of autoimmune diseases. And what you begin to see is a hint in the literature. With the onset of stress, you activate the immune system. With the onset of lots of stressors, where you activate the immune system over and over, you increase the likelihood of the immune system activating to the point of overactivating into autoimmunity. Thus, what you see is a relationship between lots of stress and flare-ups of autoimmune diseases. And where this has been seen most often in the literature is flare-ups, stress-related flare-ups of multiple sclerosis, which is a disease where your immune system is attacking part of your nervous system, where you have this autoimmune disease, rheumatoid arthritis, where it's attacking your joints, autoimmune disease, Graves' disease, where your immune system is attacking your thyroid gland, other ones as well. And what you have in all these cases is, with lots of stress, you increase the likelihood of spiraling into autoimmunity. Now, what you see is the evidence, very little evidence that stress can actually cause these diseases, but what you see instead is that they increase the likelihood of a flare-up after you've gotten it. Not huge effects, but nonetheless it's there in the literature. So what's going on with that? And what becomes relevant are, of course, glucocorticoids. Since they come in everywhere, glucocorticoids playing a very special role here. We've already heard they work with the sympathetic nervous system to cause that very rapid activation, but what they mostly do is something that takes a lot more time. So you've had this acute stressor, and you activate your immune system. Stressor is over with, and what you got to do is coast the immune system back to where it came from. Recovery. And what glucocorticoids play a large role in is the recovery process. Just like in that earlier lecture, glucocorticoids during the recovery phase after a stressor, increasing appetite, in this realm, glucocorticoids have something to do with mediating the immune stress response. They've got more to do with recovery from it. So that's great. But what if you've got a disease problem where you don't secrete glucocorticoids at that time? And this is an important transition because ad nauseum now we've been considering the circumstances where there's too much glucocorticoids. What if there's not enough now? And what you've got is, what if you don't get that recovery going on quite as well? And what you would immediately predict is you may be getting into trouble there with an increased risk of autoimmunity. And a number of years back, an endocrinologist named Alan Monk of Dartmouth University, a titan in the field and a man who I deeply, deeply respect, came up with a fascinating theory, which was, if you see disorders where you don't secrete enough glucocorticoids during stress, you see an increased risk of autoimmune disease. And this was viewed as wildly nutty and theoretical and implausible at the beginning, and research since then have shown, both in humans and in experimental subjects, animal subjects, that there are all sorts of circumstances where if you don't have the normal rise of glucocorticoids during stressors, the normal rise that will coast the system back to baseline, you increase the risk of the immune system spiraling out of control into the realm of autoimmune disease. So we're suddenly in a very different realm here after the endless cases where you get in trouble because of an excess of glucocorticoids. Here, for the first time, we're dealing with what if you don't have enough glucocorticoids, enough of a stress response, you are prone towards autoimmunity, you are prone towards too much inflammation, just to mention a disease that I don't really want to go anywhere near, but where there's hints that this might be what's going on, fibromyalgia. All sorts of inflammatory pain throughout the body. Nobody really knows what's going on, but one important thing that has popped up, there tend to be lower than normal glucocorticoid levels in people with fibromyalgia. So I'm not going anywhere closer to that. This is a very, very confused, unclear, controversial subject at this point. Okay, so we've got this picture here now of, with the onset of stress, you activate the immune system, wonderfully adaptive. Not only are you generically activating innate immunity, that inflammatory stuff, but it's fancy. You're sculpting out old, grody, white blood cells, immune cells that aren't doing you much good under the circumstance. You're really focusing in on what's needed. You're mobilizing these cells to the injury site. All of that is great. And as we've just seen, if you don't secrete enough glucocorticoids, you are in danger of spiraling into autoimmunity. So we've got a vastly confusing point here, because what we've just seen is not enough glucocorticoids, more at risk for autoimmunity. But a few minutes ago, we have lots of stress, parentheses, probably lots of glucocorticoids, and you're more at risk for autoimmune problems, autoimmune flare-ups. This seems rather contradictory and paradoxical. Too much glucocorticoids, too little, and you've got autoimmune problems. Here's a very, very, very rough solution. And this has to do with that same point we had in the lecture about appetite. You say, I am chronically stressed 24/7, and as we saw, that's not chronic stress. Whole body burns are chronic stress. What we are saying when we say, oh, chronic stress, is a lot of those episodes of transient stressors, intermittent stressors. And what we saw with the appetite realm is that problem of you've got a lot of transient stressors and you've got a lot of periods of recovery. So what you wind up seeing is, with just the right amount of these transient stressors, what you are beginning to bias towards is eventually not having the glucocorticoids doing exactly what they should be doing and perfectly and mediating that recovery period, and you are in danger of spiraling into autoimmunity. And what you also see is get just the right pattern of an excess of glucocorticoids and you can get into the same trouble, immensely complicated field. And relevant to that, Hans Selye, that guy discussed in the first lecture, the guy who's one of the founders of the whole field, Selye got as confused as everybody else as to what glucocorticoids are doing with the immune system, and he made a massive mistake in the 1950s predicting how something was going to work with glucocorticoids and immunity, and it's generally acknowledged that the sheer visibility of that massive mistake had a lot to do with the fact that he never got a Nobel Prize. This is tremendously complicated terrain. So what you see with excessive stress, not lots of the intermittent stressors, but major league chronic stress, is something very different. Not only do glucocorticoids with each stressor get secreted and bring the immune system back to baseline, but with enough stress, you now have the immune system not only going back to baseline, but being suppressed below where it normally is. And you have this grave phenomenon of immunosuppression. Short-term stress, you enhance immunity. More sustained stress response, after enhancing immunity, you return to baseline. Major league chronic stress, and you actually suppress the immune system. And this goes back to, in fact, Selye in the 1930s, once again, one of the first signs of stress-related disease. We heard the main, most famous one earlier on, which is stress increases the risk of ulcers. We now know how much more complicated that is, but stress and ulceration. You saw a second indication, or rather Selye spotted a second classical sign, which was chronically stressed animals got adrenal glands that were bigger. How come? Because they are working like crazy, pumping out epinephrine and pumping out glucocorticoids. They're working more, they get bigger. But he noticed a third sign that was part of this trio of stress-related disease back in the founding years, which was an immune glands, like the thymus gland, shrink. They atrophy. So we had that first triad, ulcers, adrenal hyperplasia, hypertrophy, and atrophy, shrinking of immune glands. And that absolutely reflects this whole phenomenon of chronic stress, and you are going to massively suppress the immune system. And you get things like the thymus. This is not a subtle effect. Just to give you a sense of this, have yourself a really awful, stressful 3-day weekend, and you're going to come back at the end of it, and your thymus gland is going to be a quarter of the size it was on Friday. This is not subtle. This is like saying, oh, psychosocial stress, and I wipe out 3 out of the 4 chambers of my heart. These are big effects. And a lot of attention has gone into figuring out how this occurs, and it's glucocorticoids, and with chronic major league stress, they do all sorts of interesting things. One of the things they do, incredibly hot subject in this field, one that seems quite bizarre, is glucocorticoids kill some cells of the immune system, and how they do it is they turn on genes called suicide genes. They get the cells to do themselves in. There's a painfully fancy term for this process of cells committing suicide. It's called apoptosis. Don't write that down, but it's very, very trendy at this point. But we've got this general theme here. Acute stressor, you activate the immune system. More sustained, you go into the recovery phase of glucocorticoids bringing you back down to baseline, more sustained major league stressor, and now suddenly forget going back to baseline and you get profoundly immunosuppressed. And this begins to explain a very, very major piece of clinical medicine, which is when you've got an autoimmune disease, when you have an inflammatory disease, you want to give somebody glucocorticoids, not some piddly amount to kind of coast it back down to where you started from. Remember, what an autoimmune disease is about is massive overactivity of the immune system, So the notion there is throw in boatloads of glucocorticoids, so it's coming out the wazoo of this person, and what you take is this way overshoot of immune activity into autoimmunity, and you coast it back down. In other words, give somebody synthetic glucocorticoids, and you may be able to do very helpful things for their autoimmune disease, their inflammatory disease. So what are we talking about here? We're talking about synthetic glucocorticoids, also known as corticosteroids. In the everyday sense, when somebody is, quote, put on steroids because of their MS, their rheumatoid arthritis, they're being given glucocorticoids. And we know some of these synthetic ones, hydrocortisone, prednisone, dexamethasone. What you're doing there is taking advantage of sledgehammer of a glucocorticoid dose, and you take this disease of overactive immunity, hyperinflammation, autoimmune attack, and you coast things back down to baseline. Just as a qualifier here, as a caveat, when talking about steroids in this case, these are not the androgenic steroids that get you thrown out of the Olympics. That's the world of testosterone. In this case, steroidal hormones, glucocorticoids are also steroidal. When somebody is taking steroids for their rheumatoid arthritis, they're taking synthetic glucocorticoids, huge doses that are bringing you back to baseline when things are too active. So we see this world where a little bit of glucocorticoids activates the sort you get with transient stressors, a ton of the stuff, way more than your body ever generates during stress, and you can take an overactive immune system and bring it back down to baseline. So think about all the lectures that came before this and all the bad things that glucocorticoids can do when they're in excess. And what you wind up seeing is take these high doses of these synthetic glucocorticoids and you begin to get a lot of the problems that we've heard about in the prior lectures. You get a lot of side effects. Okay, so this very complicated world of stress and autoimmunity and immune suppression and the therapeutic use of synthetic glucocorticoids. Now, somewhere in there, though, you focus on that fact that sort of major stressors, not synthetic glucocorticoids, but major stressors, and you can get your immune system to the point of being suppressed below normal, and suddenly you have the cornerstone concept of psychoneuroimmunology, which is insofar as lots of stress can suppress immunity, lots of stress should impair your immune defenses. And now there's all sorts of infectious diseases that should mow you over. And what's known now a few decades into this field of psychoneuroimmunology is that's exactly how it works for the relatively boring stuff. For example, with chronic stress, the common cold becomes more common. And we all learned that anecdotally back in college, where enough all-nighters right before exams, and 30 seconds after you come out of your final, you come down with some horrible cold there. Chronic stress increasing your risk of a cold, impairing your immune defenses against rhinoviruses, how you get nose colds. And this has been well studied in experimental settings and studying immune defenses against rhinovirus infection and the effects of stress on it. One of the most charming examples of how people have studied this was what used to be this research unit in England, their famed cold unit, where volunteers would come and spend a couple of weeks at this idyllic sort of country club research facility where you can either wind up being a control or an experimental, and no one would tell you which you were. And at some critical point, they would spritz up your nose, either some placebo or some spray full of rhinovirus, and then they look at various manipulations involving stress, involving stimulation, involving sociality, whatever, and see who gets the nose colds. And they would do, for the most part, very simple things and like wonderfully relaxing. Some of the folks got the lousy experiments where they had to, for example, test the hypothesis, does getting really cold, your body cold, impair your defenses against rhinovirus? They would make subjects stand out there and dump cold water on them while they're standing in their skivvies, and turns out the stressor of hypothermia increases the risk of a cold. Wonderfully insightful studies getting at the mechanisms by which Chronic stress can increase your chances of a cold. This facility, this cold unit, was apparently wonderful. People would have a great time at them, unless they got the horrible nose cold standing there in the ice bucket. People would fight to get invited back there. More than one couple emerged from people being there at the same time, where they came back and honeymooned at the cold unit. People get some very surprising realms of pleasure out there. Okay, so chronic stress and the cold. Other realms, chronic stress and another world of viruses that infect us and then go latent. For example, herpes viruses. You get a herpes infection and you get a flare-up and then it goes latent for a month, for 50 years, and what's known is one of the things that triggers herpes reactivation, sustained stress. And remarkably, this covers all sorts of realms in rats, social stress, radiation in humans, bereavement, all sorts of things like that. And you activate herpes viruses out of latency. This is brilliant on the part of herpes, because what you want to do if you're herpes is take advantage of when the immune system is suppressed by stress. Quick, make a run for it, come out of latency, make lots of copies of yourself, and then go hide again. And remarkably, viruses like herpes virus, it's been discovered, can actually measure your glucocorticoid levels. That's amazing. So we've got stuff like chronic stress with psychoneuroimmunological canonical knowledge there, and it can increase your risk of a nose cold. It can increase your risk of a viral reactivation. How about some bigger stuff? How about, for example, an HIV infection? Somebody is infected with HIV and it is now transitioned to overt AIDS. And what's AIDS about? It's about declining immune function. If you are majorly stressed, does the immune system decline faster, more severely? The jury's out on that one. It looks as if certain personality types, when crossed with major stress, and you get an acceleration of that. But now we come to what is absolutely the biggest subject in this whole field of stress and psychoneuroimmunology. The biggest subject, the most important one, the most controversial, the one that really, really dominates some folk wisdom about psychoneuroimmunology. What does stress have to do with cancer? And that will be the subject of the next lecture.
Lecture 11, Stress and Cancer.
We're roughly halfway through this course, and at this juncture we come to the topic which in some ways is the most difficult, I think emotionally the most difficult, a subject that's very complicated, very ultimately sad, which is, what does stress have to do with cancer? Now, what we saw in the last lecture, this whole world of psychoneuroimmunology, was a very simple prediction. Insofar as chronic stress can chronically suppress the immune system, if you are chronically stressed, there are all sorts of infectious diseases that you should now be more at risk of. And as we saw, that's absolutely the case for things like nose colds, for things like viral reactivation, herpes, cold sore flare-ups. What we approach in this talk is the most challenging one in this whole field. What does stress have to do with cancer? Now, in order to approach it, we need to spend a couple of minutes at the beginning here looking over what cancer is in order to see where stress impacts it. Cancer, in the broadest possible terms, cancer is a problem of uncontrolled growth. Cells that are growing much faster than they should, growing as tumors, cells that are growing at the wrong time, uncontrolled, inappropriate growth. Now, when in life do you have perfectly controlled, appropriate growth? It's during development. All you're about then is things growing, things developing. And there are all sorts of genes that regulate growth at different points during fetal life, childhood, all of that. And if everything goes right, somewhere around the points where a particular type of growth has gotten to where it's supposed to be, the relevant genes switch off. And ideally, they are now switched off for the rest of time. So what's cancer? Cancer is when there is accidental reactivation of those growth genes. Many years later in adulthood, cancer is activation of genes that have no business being active anymore. And technical term, and ignore it if you want, these genes, these growth genes which can reactivate and then cause cancer are called oncogenes. But the main point is that what cancer is about is accidental activation, turning the switch on at a point in life where the switch should not be on, resulting in uncontrolled growth in the worst places at the most inappropriate times. So what are the causes of cancers in humans? A whole bunch of the leading causes. One is radiation. One is carcinogens, xenobiotics, which are things out in the world that shouldn't be out there, various toxins. Food that is carcinogenic, food, for example, that has lots of oxygen radicals. Another major source of cancer are when you have mutations in those oncogenes where they turn on, again, when they're not supposed to. Another one is there's certain viruses that can cause cancers. These happen to be rather rare, and what you see is best evidence one of those viruses isn't enough. You have to have multiple hits. One oncogene mutation isn't enough. You have to have multiple hits. That's the basic picture of what cancer is about. Uncontrolled growth. What you get is an interesting transition in what the biology of cancer is, which is you have this early phase of uncontrolled growth, and that's all about those oncogene things that will determine if a cancer is growing successfully from the cancer standpoint. After a while, there transitions into a second stage, which is these tumors, by definition, are growing like mad at an abnormal rate at an abnormal time. They're hungry. They have very high metabolic rates, and after a while, as cancer progresses, the challenge for the cancer is not so much to activate growth, but to feed the cells. Highly, highly elevated metabolic rates. So one of the things you see with cancer as it progresses is this wild phenomenon, which is cancer cells, tumors, can give out signals which trigger the ingrowth of blood vessels, of capillaries, to supply more nutrients to the tumor, a process called angiogenesis. And a very exciting field of cancer therapeutics these days is the notion of finding angiogenesis inhibitors. If you got a growing tumor and you make it impossible for it to get a new source of energy, you're going to starve it away. So what are some of the classic defenses against cancer? Early phases are immune defenses. And we heard in the last lecture, one class of immune cells, natural killer cells, which can go after cancerous cells. There's factors released by immune cells, tumor necrosis factor, things of that sort. With any luck, they can spot a tumor when it's just beginning to be tumorous and wipe it out. So the early stage of defenses against cancer are these immune defenses. As the cancer transitions to that more mature stage, the one as just talked about, where the main thing the cancer is about is getting enough food to grow like crazy, some of the body's defenses are built around trying to starve that tumor. Okay, so that's a general, of course, highly simplified picture of what cancer is about. So now we transition to what stress does to the system. And all we have to do is have stayed awake during the last lecture, and you know the answer. We have the early phases of cancer defenses built around the immune system being active and doing what it's supposed to do. So if chronic stress is dramatically inhibiting the immune system, chronic stress should impair your defenses against cancer. QED, case closed. And it's not hard to construct a sequence there that seems irrefutable, which is lots of stress, and thus you suppress the immune system, and thus your defenses against cancer are impaired, and thus you're more at risk for cancer and tumors grow faster. Absolutely clear sequence: stress to bad immune system to bad defenses against cancer to uncontrolled cancer. Perfectly straightforward. Of course, it's going to turn out to be wildly unstraightforward as we begin to consider the subject. So what's going on? What's going on in terms of cancer progression? In terms of this simple prediction that lots of stress puts you more at risk for cancer? It's obvious how it works. It's very straightforward. Everybody knows how this works. Everybody knows that stress causes cancer. Stress causes cancer. Stress increases the risk of getting cancer. Stress, once you have cancer, makes tumors grow faster. Stress is more likely to cause cancer relapse. Everybody knows this. It's one of the most commonly held beliefs about how cancer biology works and how stress-related disease works, sufficiently so that some years ago, there was a paper published in the journal Psycho-Oncology, the interactions between psychology and the cancer process. This paper in 2001, where a bunch of women who had just gotten a very serious breast cancer diagnosis were asked something simple. So what do you think caused your cancer? And we saw a few minutes ago all sorts of possibilities, radiation, carcinogens, mutations, all of that. And by a wide margin, what was the most common answer? Stress. Stress caused my cancer. So we've got this deeply held belief here that stress can cause cancer. So now it's time for us, amid that picture, to start dissecting this belief. First off, what's going on with animals, experimental animals, the world in which you can understand cancer in its greatest detail, the experimental setting in a laboratory, what is found there? Yes, indeed, lots of stress, lots of glucocorticoids. They, of course, were inevitably going to come in on the scene. Lots of stress, lots of glucocorticoids increase the risk of cancer in laboratory animals. And once they have the cancer, what stress does is accelerate the progression of the tumor. And it's reasonably well understood how this works, involving immune defenses being impaired, involving some of those metabolic defenses being impaired. It's reasonably well understood. My lab, in fact, did some of that work some years ago, perfectly straightforward. So we appear to have this slam dunk in the world of experimental laboratory research, stress and cancer, they seem interlinked. So what about humans? What about humans in a broad way? And what we've got right off the bat here inevitably is a really complicated picture. Right off the bat, what we have is lots of reasons to pay no attention to those laboratory studies. For a very simple reason, what causes the cancer in these animal studies? For the most part, you can't sit around and have the 10% of your rats as they get older come down with spontaneous cancer. It's really hard to study that. What you do is you experimentally induce the cancer. What you do is take some cancerous cells and inject it into the lab rat, and cancer occurrence, what that's about is whether those cancerous cells take off as a tumor. What cancer progression is about is how fast that tumor grows then, and human cancers are, no surprise, not due to being injected with tumorous cells, as we heard already, viruses, pathogens, radiation, all of that. So immediately there's this disturbing issue as to whether any of the laboratory stuff with lab rats are in fact pertinent to human cancer. So now what we need to do is very carefully dissect what's actually going on. And this is a particularly tough field because, as noted already, lots of folks go into it with some beliefs about how things work, and it has taken some enormously obsessive, aggressively detailed-oriented research to try to pick apart this issue in humans. Some really hard work calling into play epidemiologists who look at patterns of disease in people, statisticians, God help us, who play a critical role figuring out were data analyzed the correct way. Very, very challenging field. So what do we know? First off, what do we know in humans about stress increasing the incidence of cancer? And this appears to be pretty straightforward, which is there is indeed an increased incidence of people with a stress history having a higher likelihood of coming down with cancer. And probably the major stressor that's been studied most frequently is major depression. And as we will see in a few lectures, you cannot begin to understand what's going on in depression outside the context of severe stress. So depression, other stressors, increasing the risk of cancer seems absolutely straightforward, from the cancer is due to stress to all the other ways in which people believe there's a connection. This appears to indeed be the case when you look at the data. But there's a problem. There's a problem that's already popped up in a number of these studies and a number of these disciplines that we've heard about, which is these studies are mostly retrospective. In other words, somebody comes down with cancer and you then find out what stressors did they have in their life. Or even more shaky, they come down with cancer and you ask them what stressors have they had in their life. And what we saw in the previous lecture is there's this problem. There's this problem, which is when something bad is going on, our memory is preferentially focused on bad things. When something is awful as a cancer diagnosis is going on, and you ask people to say, well, have you had a lot of stress in your life in recent years? People will preferentially remember the bad stuff. And we saw that in the previous lecture, that wildly unlikely who approved this experiment where people were made to have chronic stomach problems experimentally. The doctor tells them, not truthfully, they've got an ulcer, was anything stressful going on, and suddenly you remember all sorts of stressors. Retrospective data are very, very shaky for those reasons. Even retrospective, like going back through medical records. And what you see is when you look at cancer patients versus people without cancer, cancer patients remember more stressors prior in life when you control for did these two groups actually have the same amount of stress. Cancer patients, a higher rate of remembering stressors than non-cancer patients. Patients with severe cancer at a higher rate than people with less severe ones. Huge problems with this retrospective literature. So then we switch over to what's the gold standard of these sorts of studies, vastly more difficult, what are called prospective studies, which is you sit down with a bunch of people who don't have cancer, who, in order to qualify for these studies, in fact, appear to be perfectly healthy, and now you follow them over the years and see if they come down with cancer. Prospective. You need vast numbers of people in these studies because the incidence of cancer in the time span of these studies tends to be rather low. You need an enormous amount of resources to do these studies. This is the gold standard, doing a prospective study. So when they're done, what has come out of that literature? Number of studies suggesting that, yes indeed, prospectively, lots of stressors in life increase the risk of cancer. But these studies often have some problems in them. For example, there's this one classic one that everybody learned about as this field first emerged, a study of a large number of people working in a Western Electric plant, I believe in Buffalo in New York, where prospective study, and what they showed was focusing in on a classic stressor, as we've already heard, major depression. And what they showed was major depression, as you prospectively go through the study, major depression caused a twofold increase in cancer risk. Not good, seemingly an absolutely clear, irrefutable connection here between stressors and cancer risk. So that one's the iconic demonstration of it, the classic one, and some years after it was carried out, a very subtle, energetically detailed, focusing, statistically wise guy went and analyzed just the hell out of these data and discovered a very interesting confound in there, which was the people who were working in this Western Electric plant who were getting depressed were mostly getting depressed because they had an awful boss who had them working under unsafe working conditions with lots of exposure to carcinogens. Oh, well, that's kind of a confound. That's kind of hard to evaluate then. This classic study down the drain then in terms of showing a cancer connection. Okay, what else might come out of these prospective studies? You might ask, well, do people who have stressors, Do you begin to see changes in immune function? What we know is changes, suppression of immune function in a way that now puts you more at risk for cancer. And in general, what these studies have shown is you don't get enormous decreases in immune function. Yes, in the last lecture we heard chronic stress, you can suppress immunity enough that you're now more at risk for a nose cold. Seemingly, the stressors that we think of as increasing the risk of cancer, they don't suppress the immune system anywhere far enough. Because the reality is you need to absolutely flatten the immune system to seriously increase your risk of cancer. And this is seen, for example, in HIV, people with AIDS, and one of the things you see is an increased risk of certain types of cancers, one called Kaposi sarcoma. This used to be a cancer you would see in 80-year-olds once in a career, and suddenly it's popping up in a lot of 30-year-olds with AIDS. Okay, severe immune suppression increases the risk of cancer. All things considered is the fact that the immune system is just ground down to nothing in HIV, and only a relatively small subset of AIDS patients come down with this cancer, making that same point again. You've got to absolutely push the immune system down to the floor, and on the simplest level, stressors just don't do that. So now we have a greatly weakened viewpoint of stress increasing the likelihood of getting cancer. Okay, how about the next realm of stress? How about the notion that certain personalities increase the risk of cancer? And this has been a wildly controversial field. There has been a long-standing view that there is a certain personality type that increases cancer risk, and these are individuals who are introverted and repressive, and especially repressive about anger, and minimal evidence for this. Minimal evidence, and one of the big problems is that that literature has relied very heavily on retrospective evidence. Furthermore, you see no evidence that these folks with these repressive, cancer-prone personalities have anything screwy about their immune systems. So in general, the literature showing a link between certain personality styles and cancer risk has been pretty unimpressive. Okay, so what we've seen now is there's not a ton of evidence for cancer, the likelihood of getting cancer, the incidence of cancer being stress-related. How about the next step in the progression? You've had cancer, there's been a successful treatment, the cancer has gone into remission. Does stress have anything to do with the likelihood of a relapse, the cancer coming out of remission? And what you see is minimal evidence at best. So now we move over to what in lots of ways is the most controversial issue in the field, which is not what does stress have to do with getting cancer, not does it have to do with a relapse, but what does stress have to do with the rate of progression, the rate at which the cancer grows, the rate at which things get worse. Can stress accelerate cancer progression? And this one is wildly controversial, except on first pass, it doesn't appear to be very controversial at all, in that there seems to be some fairly good evidence showing that stress can accelerate cancer progression. Now, the best evidence for that, the one that most caught sort of the public attention and seemed to just reify stress cancer, is to go in with a certain experimental style, which is intervene with cancer patients, do something or other that decreases their levels of stress, and does that slow down the cancer progression? And some studies have looked at this, and there is one classic one carried out by a colleague of mine at Stanford named David Spiegel, who did the study which was published in the late 80s, New England Journal of Medicine, and before it was over with, it was front page news all over the country. Here's what he did. Women who had just gotten a metastatic breast cancer diagnosis. And Spiegel had these women randomized into two different groups. First group got standard medical treatment for the cancer. Second group got standard medical treatment, plus they joined a cancer support group that had intensive group therapy a number of times a week. And when he broke the code, out came the finding that the women who went into the cancer support setting an average of 18 months longer survival than the other group. This was a huge finding. This was a dramatic effect. This was amazing news. And this was immensely exciting. And part of what was immensely exciting was it was absolutely clear how the underlying biology of this would work. And we've already heard this. Nice supportive group setting of therapy with other cancer patients make you feel less stressed. Thus, your immune system works better. Thus, you're better at fighting the cancer. Thus, you live 18 months longer on the average. Amazing finding, one that just had a huge impact in the field. So what has happened since then? Roughly half the studies that have been carried out since then support the finding, showing that supportive group therapy, various psychotherapeutic interventions slow down cancer progression. About half the studies haven't replicated it. So what's going on there in the cases where, yes, indeed, you are slowing down the cancer progression? What's going on there? Obvious sort of pathway again, better immune defenses thanks to less stress, all of that. Spiegel and his group have looked at whether there are indeed changes in immune function in women with these supportive settings. And there are some changes, but they don't particularly correlate with the cancer outcome. That's been less clear. So what's actually going on here? What's happening? And what we have here is something extraordinarily subtle and very tough to get at. And this is something where Spiegel has been one of the leading thinkers in this area. And this is a man who has a wonderfully sort of research integrity in terms of not getting pulled in by the easy explanations. What might actually be going on? And here we get into what is one of the dirty secrets in cancer therapeutics. Okay. You have cancer and you're going through treatments, chemotherapy, radiation therapy. It is absolutely clear this is your best chance. Go through it, power through there. And it turns out an awful lot of people with types of cancer seriously diverge from what their treatment is supposed to be like. They are not as compliant as they are supposed to be. They fail to take their medications. They miss doctor's appointments. Something like a quarter of cancer patients seriously diverge from their treatment regime. Why is this a dirty secret in the field? It's obvious. You've got cancer. There's this whole sort of structure in the field, type C personality, people with cancer who are going to fight, and not let the cancer do them in. And if there's a treatment that might help, do it twice as much and just power through there. And suddenly, you got people with cancer who aren't taking their medications as much. Ooh, this looks really bad. Secret, dark secret, very rarely dealt with. Why does this happen? It's obvious why it happens, because most of the cancer treatments make you feel so sick and so awful that it's hard to comply entirely. So what happens in this cancer supportive therapy context? What you've got there is you're sitting around with a bunch of other people going through the same hell you're going through, and they all support each other. And they support each other in terms of compliance. Sitting there saying, did you take your meds today? I know I hate them too. They make me totally nauseous, but you know what? We're both going to take them right now. Have you eaten today? Yeah, I have no appetite either, but we are going to eat. Right after this, you are going to the doctor. You're not going to skip that appointment. When people are in that supportive setting of other cancer sufferers where they're cheering each other on, people become more compliant. And in lots of ways, this might be what's going on in this literature. And again, this is not a stress reduction, better immunity, less cancer. This is a completely roundabout way. What seems to have been one of the strongest links between stress and cancer, it's instead probably a compliance issue. Okay, so of all the classes, all the topics we've had so far, this is the one where I've probably spent the most time going after individual subject, going after it in detail. Why is this important? Why is this such an important topic to go after? Remember that 2001 study. Remember that one where the women with breast cancer asked to attribute their cancer to something or other, and the most common answer was stress. And somewhere in this, urban legend, this folk psychology, somewhere in there with this erroneous connection between stress and cancer, something very dangerous and damaging occurs. Something which, frankly, there are all sorts of highly credentialed charlatans out there who take advantage of it. And we know this world, people who flog the notion that here's my brand of stress management, credit cards accepted, that will slow down the progression of your cancer, that will stop your cancer from growing, that will completely reverse it. And what we have here is very little, if any, scientific evidence linking this. And these are not crackpots off on the periphery. These are often some very influential and credentialed medical, biomedical experts. And there's one particular one I want to focus on. And I will bypass his name just out of sort of legalistic prudence here. But this is an individual, a Yale-trained physician, who in the late 1980s had a wildly successful best-selling book looking at this notion, advocating the notion that stress causes cancer, and thus stress reduction can slow down cancer progression. And just to be really careful about this, as I read some quotes from this man's book, I am going to actually have them here just so I get them right. Here are some of the quotes in thinking about the causes of disease, the causes of cancer. Quote number 1, the fundamental problem most patients face is an inability to love themselves. Next quote, she chose the path of life, and as she grew, her cancer shrank. Next quote, patient, I decided to live to be 100 and leave my troubles to God. I really could end the book here because this peace of mind can heal anything. In other words, if you have cancer and it's out of control and it's doing you in and it's killing you, why is that happening? Maybe because you're unable to love yourself, maybe because you didn't choose the path of life, maybe because you didn't grow in the face of adversity, maybe because you decided that you weren't going to leave your troubles to God, maybe because you really didn't want to live to be 100. All these attributions here, all these blaming the victim. And in lots of ways, this person's philosophy is most aptly summed up in, once again, a direct quote, and one of the sort of main ones in this book, quote, there are no incurable diseases, only incurable people. And what are you teaching someone when this is happening? You've got somebody on their deathbed with their terminal cancer that has resisted the treatments and progressed, and what this viewpoint teaches is, while you're lying on your deathbed, ooh, too bad I didn't have different priorities in life, too bad I didn't control my stress, too bad I didn't choose life, too bad I couldn't love myself sufficiently. This is where you wind up. Would that it be so that these sort of interventions could cure cancer if only cancer could be stopped if we were sufficiently brave and sufficiently tenacious and sufficiently filled with love? It doesn't work that way. And this view being flogged by folks who are not crackpots out in left field, but again, often highly credentialed experts, the science simply isn't there. Amid all the diseases that we've had to think about in this course so far, all of these diseases where stress plays an adverse role, this is a domain where it doesn't count. And if you really push the view that it does, ultimately, bad science, bad medicine, ultimately bad ethics, and shame on anyone who would profit from this.
Lecture 12, Stress and Pain.
In this lecture, we're going to look at a subject that's utterly intertwined with stress, which is pain. And this is bidirectional. Stress can cause you to change your sensitivity to pain. Pain constitutes a stressor. We're going to look at the interaction between the two. Okay, by now you know the drill sufficiently so that They could come in here and deflate me and put me in a storage closet, and you could leap right in and go through the dichotomy, short term, stress response is good news, bad long term, it's bad news. As we're going to see, the biology of pain, this is the one exception. All right, so we start off with pain. We all hate pain. Pain's a great thing to get rid of. Pain is bad news. Pain is remarkably good news and remarkably helpful when it's occurring at the right time. You generally want some sort of signal coming from the periphery saying, ooh, my big toe is in the fire there. This might be a good time to move it backwards. You need pain signaling you in circumstances where you can fix the situation. And there is a terrible disease where people are born, a rare one, without the ability to feel pain. And what you get is all sorts of things go wrong, even to the extent of these are people who damage their legs, damage their knees because they don't get the pain feedback telling how much force you should be descending a flight of stairs with. So pain is wonderful when it's occurring in a circumstance where you can actually change your behavior and decrease the source of damage. And as we would well know, when it's circumstances where there's nothing you can do, pain is a misery. Pain is a nightmare. So how does it work? Shifting over to the biology of pain so that we can then appreciate what it is that stress does, pain is actually quite well understood. It starts off with all sorts of outposts in your body, all sorts of sentinels, all sorts of sensors that pick up when something is going wrong. And this could be on the level of your skin. It could be on the level of muscles when you have muscle pain. It could be in various organs when suddenly you have a stomach ache, when suddenly something else feels more serious. In all these cases, what you have to have is something is responsive to a pain signal out there, and it is then able to send that information to your spinal cord and up to your brain, and there you go. So what you have to have are pain sensors. And pain comes in all sorts of different forms. You have sensors, for example, that are sensitive to extreme heat. They will pick up a signal of heat somewhere on your skin, wherever it's relevant, and these receptors, these neurons, these brain cells, these are brain cells out in your skin. This is your nervous system sending projections everywhere. You have these specialized heat-sensitive neurons that pick up that heat, activate, and send the signal on down. Meanwhile, not surprisingly, you have other receptive neurons that do just the opposite. They're sensitive to cold. Meanwhile, there are other ones that are sensitive to pressure, extreme pressure. Ouch, somebody is squeezing your hand. So pressure transducing neurons there, which take that sort of signal and turn that into a different sort of pain perception. There's even pain neurons that respond to things like you've just gotten cut. And this is really a weird one when you think about it. There are certain chemicals which are found inside your cells. And as a general rule, if they're found outside the cells, that's a bad sign because something has sliced that cell open. And as a result of the innards of that cell spilling out, that particular chemical binds to a receptor in another cell nearby and sends a signal, we've been cut. Why is that bizarre? Because what that winds up meaning is when you accidentally get a paper cut and it hurts, you literally are slicing some cells in there in half where they are spilling out their guts. So different types of pain. Very interestingly, there turns out to be an additional type of pain, and this is one that initially seems metaphorical and turns out to be much more literal. You are eating wildly spicy food to the point where it hurts. You've got sweat running down your nose, and you're taking great pleasure in this. Very spicy food hurts. And spice is mediated by a chemical found in spicy food called capsaicin. And people long wondered why spicy food at an extreme can hurt, why spicy food tastes hot. And remarkably, it turns out that this capsaicin, this chemical found in hot peppers, actually activates some of those hot receptor neurons. Spicy food that is hot is literally activating a hot pain system. So how does this work once you've gotten past these receptors? Once you've gotten past that first phase? How is it now processed in your spinal cord on up to your brain? And to appreciate this, we need to shift over to a diagram that's in your guidebook, one that is the dominating model in the field. Wonderful, wonderful insight as to how this system works. In this diagram, we start with part A, up on top. And what we've got are projections of neurons talking to other neurons. Do not panic. This is highly schematic. None of your neurons look this way. What we have is a neuron sitting there in the middle, the one marked X, which sends a projection to the brain. This neuron is sitting in your spinal cord. And when it is stimulated, it sends a signal telling your brain that there's something painful happening. So when does it get stimulated? And you see there are the projections above and below neuron X, those lines coming from neurons somewhere to the left of this diagram. What sort of neurons are those? Those are the pain sentinels. Those are the cold responsive, hot responsive, pressure responsive. So there's two different types of pathways that could wind up stimulating that neuron X. First one, shown up on top, mediates sudden pain. And we see that projection coming from the imaginary neuron on top to the left, its cell body, projecting, sending this cable-like projection to neuron X. And what it does there is it stimulates neuron X. When the neuron that mediates sudden pain gets activated, it stimulates and activates neuron X. Meanwhile, down below in the same diagram, you've got a slow pain pathway, and that's coming from a different type of pain receptive neuron, which activates in response to painful stimulus, activates that pathway, which stimulates neuron X also. And soon, your brain gets information that something painful has occurred. This doesn't explain much. And where the subtlety, where the beautiful elegance of this model comes in is now we transition over to the B part of the diagram, because it's a little more complicated than what I showed you. Now we've got a second neuron on the scene, neuron Y, also found in your spinal cord. Neuron Y sends a projection to neuron X. And what neuron Y does is it inhibits the activity of neuron X. It makes neuron X less excitable. So look at what's happening. Back to the sudden pain pathway up on top. Your sudden pain-oriented receptors responding to things like a cut get activated and, as we just saw, send that signal to neuron X and stimulates it. And you feel pain. But at the same time, that same sudden pain neuron up on top has a collateral, a cable that comes off, which also sends a projection to neuron Y and stimulates it. So what happens here? The pain receptive neuron up on top gets stimulated by something painful and stimulates neuron Y and X at the same time. And then with a slight delay, neuron Y turns off neuron X. And what have you just explained? Why you get a sharp, piercing pain, which then goes away shortly afterward. You touch a pot that's hot and you pull your finger back, you get a paper cut and it suddenly hurts and then it goes away. And that's all due to the fact that with a delay, neuron Y is turning off neuron X after that excitation. Meanwhile, still in diagram B, underneath, you've got that slow pain pathway when some pain-evoking stimulus that we tend to subjectively feel as being slow activates that neuron, as we saw before. The projection comes in and stimulates neuron X, you're feeling pain. And just like before, that same neuron has a branch, a collateral going off to neuron Y. But this time, what that collateral does is it inhibits the activity of neuron Y. So what happens? Something painful occurs, activates neuron X, which gets excited, sending a pain signal. And what you're also doing there is you're shutting down neuron Y, which makes it impossible for neuron Y to shut down neuron X. What happens? The pain keeps going. It throbs. This is what chronic throbbing pain is about. So two very different pathways that are pulled out of this diagram. Now this begins to explain a couple of really interesting things. What this tells you is, suppose you've got a throbbing chronic pain, which is neuron X is activated and neuron Y doesn't have the means to silence neuron X. What would you love to do? Let's stimulate Y so it kicks in and shuts off X. When is that going on? You have a chronic pain, which is what itching is in some circumstances. You've got some horrible itchy mosquito bite. And what do we often do? Don't scratch the mosquito bite. It'll get infected. What you do instead is you scratch on either side of it. And what you're doing is you're stimulating that sudden pain pathway, which stimulates Y, which silences X, and the itchiness goes away for a little bit. Another example of this. Suppose you have a chronic pain, throbbing, coming from that lower slow pain pathway, and you want to make it go away, some throbbing pain in your muscles. What do? You go get somebody to pound on your back hard, give you a massage. Because what is done with a really aggressive massaging is you stimulate those acute pain pathways, which activates Y to silence X. Even more examples. You've got a condition where somebody has a lot of trouble delivering energy to cells throughout the body. We heard about that earlier. That's what juvenile diabetes is about. And as a result of that energy depletion, some of your cells begin to die. And for very complex reasons, in a pathway like this, it's the sudden pain pathway neurons that die. What's the consequence of this? You turn on a slow pain pathway, and Y shuts down, and X keeps screaming its head off for long afterward, and it just keeps going and going because you can never shut down that signal with a sharp input. What have you got? Diabetic neuropathy, the fact that pain there just goes on and on. So here we've seen the basic wiring of the system. So how does it begin to play out? There's all sorts of interesting things that happen that underlie an important fact there, which is pain is not that objective of a state. There's a lot of subjectivity that comes into pain perception. For example, you can have a circumstance where you feel pain and there's not even a stimulus, a painful stimulus happening. And a lot of us feel that pain, which is when you're in the dentist chair and the person so much as walks in the room and your teeth are aching. There was no stimulus there. And if you're really hypersensitive, you feel throbbing pain in your gums there simply by hearing the music going on in the office. So that could be a source where, with no actual stimulus, you're feeling pain. Some of those neurons are sending messages up to your brain when there was nothing that stimulated them. Another example, you sit there and instead of experiencing some pure, overt, realistic pain stimulus, hot, cold, whatever, you sit there and you watch the same thing being done to a loved one and you feel their pain. On a certain level, the feeling of pain as an empathetic response, that taps into the same wiring here. As we'll see in a coming lecture, there's another example of this. Clinical depression appears to involve overactivation of a couple of these pain pathways. In other words, psychic pain even has some reality in terms of wiring. So some of the time, you can turn on a pain response when there's absolutely no stimulus. Some of the time, there can be a pain stimulus and you don't even notice it. And let me give you a highly technical example. Suppose somebody takes some really rough sandpaper and unexpectedly sandpapers your rear end over and over, abrading it. This is likely to seem unpleasant. Suppose instead, in some rare abstract scenario, you are abrading your rear end exactly the same way, having enthusiastic sex while on a carpet or whatever, and you don't even notice it. Context makes a huge difference. And then there's some settings where you not only don't notice the pain, where you actually give a subjective interpretation that the pain is good news. Some very poignant examples. First one, you have some soldier in battle that is utterly terrifying, people getting killed left and right, and the person gets shot in their leg. It hurts. This is not a fatal wound. It hurts, and why could this be good news? This means they're injured. They're out of this war. They're being sent to the back lines. This hurts like crazy, but here's the wonderful news. I'm going to survive. Or another example that is quite poignant as well, and this is someone I happen to know with a very serious type of cancer, and at some point they tried an experimental drug. It wasn't quite clear if it was going to work, and if it did work, if this drug started killing some of the tumor cells, things were going to hurt like crazy as those cells died. And a few weeks into it, yes, indeed, fortunately, this therapy was working, and talking to this friend saying, well, how's this feel? And the response being, it hurts like hell, and that's the greatest news I could possibly get. This is the sign that it's working. So there's this tremendous element of subjectivity going on in there. And how might that subjectivity work? We will see the wiring for that shortly, but what you know is going on in there is your brain isn't just getting signals from your spinal cord. Your brain is sending signals down to your spinal cord. Okay, so a bit more about the wiring. You hit one of those painful stimuli, and it is activating the sudden acute pain pathway or the throbbing dull one. Part of what happens then is exclusively in your spinal cord. You've got reflexes where a pain signal comes in, and an instant later, the spinal cord is sending a message to the relevant muscles, get your foot out of that fire. You are not sitting there consciously saying, well, that sure feels aversive, and in fact, my toe is roasting. This might be a good time to send a message. Let's see, was it my left toe, big toe, or my right one? Let's send a message there telling it to retract. It's purely spinal reflex. So that's a first level of analysis of a painful input. The next is going on in the brain. And it's a level of the brain, a very ancient part of the brain, that's telling you objective information about the source of pain. It's telling you how painful the pain is. It's telling you where the pain is coming from. This is your painometer, telling you how many units of ouchness you've gotten there. This is one that is sending up information saying it's your foot, not your hand that's gotten injured. This is a bad one. This is a moderate one, whatever. And this activates parts of the brain, which in turn tell other parts to make you start breathing faster and your heart to speed up and maybe to whimper and some of your blood vessels there to constrict, all sorts of autonomic nervous system stuff. So that's a bit of wiring that's in common to all sorts of species out there, including us. Then there's a level on top of it. And this is not the painometer, ancient part of your brain measuring how many of your toes feel miserable. This is forebrain, more recently evolved parts of the brain, your cortex, in particular an area called the frontal cortex. And what that one plays a role in is evaluating the pain, telling you what you think about it, how you feel about it. And as soon as you're in a world of people who are being in great amounts of pain is wonderful news because they're out of the war, where looking at their loved one feels painful. When you're up there, this is not the painometer part of the brain. This is that forebrain, that frontal cortex, doing evaluative stuff. What does this pain information mean? Now, in order for that to work, we have to return to that diagram, which is in the guidebook, and now we see a very important elaboration. What we've just gone through are circumstances where pain, those parts of the brain that give the subjective evaluative notion of what the pain is about, changes your pain perception. In other words, not only, as promised, is the brain getting pain information coming from the periphery, the brain is sending information back out to the periphery. And as you can see in the diagram here, part C, we've now added in an additional element. We've got the sudden pain inputs, the slow pain inputs, neuron Y, neuron X when activated, setting information up to the brain, the stuff we all know. But now what we also see is the possibility of projections coming down the spine from the brain, some of which stimulate neuron X, and suddenly the Muzak in the dentist's office is making you feel miserable. Some of it coming down, inhibiting neuron X, the evaluative stuff. This is great news. I'm out of the war now. So what we have here is this bidirectionality. Your brain is influencing how sensitive those neurons are to a painful input. So this is the basic wiring about how pain works. So what does stress do on top of it? We've already heard a bit about this in the very first lecture. Massive, painful, stressful stimulus. And this is our zebra with its innards ripped out by the predator. And one of the things that happens is, blessedly, pain perception gets blunted somewhat. Stress-induced analgesia. Analgesia, the inability to feel pain. Severe stress can block some pain perception. And this pops up, this has been documented in all sorts of fascinating ways. For example, you get people who are involved in a serious car accident, and what the literature shows is above a certain degree of seriousness, 80% of them need morphine as a painkiller. Meanwhile, you look at soldiers in the middle of a battle who get the exact same severity of injury, and the percentage that need the morphine is vastly lower. What's that about? You have a car accident that comes from out of nowhere, excruciating pain. You get the same injury in the middle of a battle, and the stress of that battle has been producing a roaringly effective case of stress-induced analgesia. And there's much more commonplace circumstances where the same thing happens. You're in the middle of the annual company volleyball game, and you come down and you twist your ankle, and you don't feel it quite as much. That's because, in this case, the stress of the physical activity has induced a certain degree of stress-induced analgesia. So that's a mighty useful thing if you are running away from that lion and you've got that bad injury. How does it work? What are the mechanisms underlying that? And it's actually quite well understood, and a big piece of it has to do with the stress hormone we've heard about a lot in some recent lectures, beta endorphins. Remember, I brought up that point, beta endorphins, they have something to do with pain, but weirdly, here's yet another hormone chemical messenger that does more than one thing. It's got something to do with reproduction, all of that. Now we get to the central arena of what beta endorphin does. And again, going back to its name, what the source of it is, endorphin, endogenous morphine. Beta endorphin is the drug that blocks the pain perception, the chemical messenger. And we can once again go back to that diagram, to part C, and you look at those projections coming down from the brain. Look at the bottom one, the one that inhibits neuron X, the one that makes neuron X less likely to activate, the one that blunts pain perception. Almost certainly in a lot of these circuits, that projection from the brain makes use of endorphins to block the pain perception. And that's great. That begins to account for the reason why most people who know what beta endorphin is about understand what it does, which is the famed runner's high, your endorphin high. You go out and you decide to run some long distance, and it hurts, and you're miserable, and you're dizzy, and you're ready to keel over. And somewhere around 10, 20 minutes into it, suddenly you get this wonderful, gauzy sense of well-being, and it's great. And that's when the endorphins kick in. Mind you, the next day you're going to be miserably sore, but for the moment at least, that's where it's coming from. There's also evidence that acupuncture, when it blocks pain perception, is doing so by stimulating endorphin release. There's also evidence that placebo effects, when one is faked into thinking that you've blocked pain, you're putting a painful stimulus, say something hot on your fingertip, and the subjects are told that they're putting on a cream which blocks pain perception. It actually doesn't really do that. It just causes a placebo effect, and you feel less pain there. And what that placebo effect appears to be about, in a lot of cases, is activating those descending beta endorphin pathways. This finger is screaming with the exact same painful, hot stimulus, and your brain is saying, hey, that doesn't really hurt, because after all, we've got this new analgesic cream on our fingertip. That's the brain sending that message down to the neuron X, almost certainly using beta endorphin as the pathway. So now we come into, instead of the realm of acute stress and the activation of beta endorphin and that whole sort of pathway and the acute tapping into that circuit, now what about chronic stress? What about massive chronic stress? And what we get to is truly bad news. Let us return to that diagram yet again. What happens with sustained stress? Major stress is really unpleasant, which is a lot of stimulation of pain pathways make pain pathways more sensitive, more responsive, so that pain begets pain. And you have a phenomenon of hyperalgesia, which is where you have enhanced pain sensitivity. There are some horrible clinical disorders where there's problems in the nervous system, the sort of wiring we've been looking at, where those neurons just fire spontaneously, and thus you are constantly in pain, the hyperalgesia. But one of the things that chronic stress can do is increase the excitability of those neurons. And at an extreme, what you wind up getting is a neuron that actually keeps stimulating itself. Let's look once again at neuron X, and we've already seen the possibility that a neuron sends its primary projection and then has one of those collateral things that come off. What you can sometimes see is something like a neuron X forms a collateral that loops back on itself, and every time neuron X gets stimulated, it stimulates itself more and more hyperalgesia. And where stress appears to come in, making this possible, is what we've heard about already, the capacity of acute stressors to activate the innate immune response. You remember that from a few lectures ago, to cause inflammation. Inflammation makes pain-mediating neurons more excitable and more likely to get into this vicious circle of pain activation causing pain activation causing pain activation. So now back to where this lecture started, which was going through our usual dichotomy, short-term, good news, long-term, bad news, and also going back to the very first lecture, going through that notion of cellulase, which turned out to be wrong. Why is it that chronic stress makes you sick? And he came up with that completely incorrect idea that with chronic stress you go into the exhaustion phase. You run out of the hormones of the stress response. You are depleted of adrenaline, epinephrine. You're depleted of this or that hormone related to stress, and you are pummeled there. And as we saw, this doesn't happen. There is no organism on Earth that has been so stressed that it runs out of adrenaline. It simply doesn't happen. This is the one domain where it appears to happen. Because what you get is, with enough pain, with severe enough of pain, with long-lasting enough of pain and stress, what do? You get depleted of beta endorphin. The beta endorphin that comes out of the pituitary, as it turns out, and works on the spine. You get depleted of beta endorphin for a very simple reason. Those cells that are making the beta endorphin, they're dumping so much of the stuff out, and they get just a little bit behind, and they can't quite keep up with demand. So the problem in this case is not the one we've been seeing over and over in lectures, which is the stress response just keeps going for too long, too much prolactin, too much glucocorticoids. The problem here is this rare case of Cellier being right in this regard. You run out of the hormone that protects you from the stressor. And what does that mean? That means something really sad and really awful, which is you get that person with a horrendous injury, you get that soldier who's just been shot, you get the woman with a terminal painful cancer, and it's not the case that eventually you turn off the pathways. What eventually happens is you run out of stuff like beta endorphin, and the pain comes back and just keeps going.
Lecture 13, Stress, Learning, and Memory.
Well, no doubt everybody out there is still reeling from the distressing digression we had in the last lecture, away from our usual dichotomy, short-term good news, long-term stress and bad news, and discovering that chronic activation of pain systems, in fact, don't occur. You ran out of beta endorphin, that whole fact that we finished with last time. What we do now in this lecture is get back on wonderful, comfortable ground. We're dealing once again with this dichotomy of ours, Short-term activation of the stress response, doing a good thing, in this case, the theme of this lecture, enhancing learning and memory. Chronic stress, doing just the opposite. Now, as with a lot of the other lectures, what we first need to do here is go over the basic workings of the system we're going to talk about. How does memory work? And what we'll do is first look at memory as a behavioral phenomenon, then how memory works at the level of whole sections of the brain, how it works at the level of individual cells, how it works at the level of networks. Now, the first important point here in looking at memory as a behavioral phenomenon is memory is not monolithic. There's not just one type of memory. If you will, there's a whole taxonomy of different types of memory. Short versus long-term versus remote memory, other subcategories. There is one that's going to be quite important here, a dichotomy between what is called explicit or declarative memory and implicit memory. Explicit declarative memory. You know a fact, and you know that you know the fact. I have a birthday in April. I am a mammal. I have a doctor's appointment next Tuesday. You know the facts sufficiently so that you can actively, consciously behave with that knowledge. Explicit declarative memory. You can declare that Was it President Bench, President Tree, President Shrub, President Bush? Bush, that's right, the kid, the son, Bush, President Bush. And out it pops, showing this characteristic early on in Alzheimer's. It's not that the memory is lost, it has taken more work to pull it out of the networks because the networks have lost neurons, the networks have weakened. So that gives a sense about how memory works at the level of whole regions of the brain, the hippocampus, and it's not just the hippocampus, but hippocampus being very notable for this declarative memory. What's going on down at the cellular level? Memory does not consist of making new neurons, does not consist of making new connections, but strengthening pre-existing ones, and how those strengthened connections play out over the course of lots of neurons, networks of neurons, making those connections with each other. Ironic ending department, it turns out, that ancient, laughable notion that memory consists of making new neurons, or even memory consists of making new connections, that's ridiculous. That's medieval neuroscience. In the last few years, there's increasing evidence that that actually does occur some of the time. A huge revolution in neurobiology has occurred for the last, centuries. If you're learning basic neurobiology, one of the facts that gets hammered in immediately is the adult brain doesn't make new neurons. You're stuck with whatever number you got early on, and all that happens from there is you go downhill with fewer of them. This revolution being that it turns out the adult brain, even in humans, does make new neurons, adult neurogenesis. And remarkably, the place in the brain where it happens the most is in, you guessed it, the hippocampus. And at this stage, there's beginning to be evidence that certain types of memory acquisition require the formation of new neurons. So here we have both learning the lessons of history and having it repeat on you. Here we are back again, the notion that some of memory formation actually involves forming new neurons or forming new connections, as it turns out. Nonetheless, the bulk of what goes on appears to be that strengthening of pre-existing neurons. Okay, so we've got basic memoryology under our belt here at the systems level, networks, individual cells. So what happens with stress? What happens? You know exactly what happens, which is short term, you have memory enhanced. Short term, stress does great things for your learning and memory. And we saw that starting in the very first lecture. Short term, what do? You increase the delivery of oxygen to the brain. You increase the delivery of glucose. Those are
More of a dog person, huh?
Tell me your secrets, tell me your story, let me in. We can start from the beginning. Let me listen. Give me the chance.
Hear that?
What?
Nothing. No birds. No animals. Nothing. 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 Nothing.
took a 40, threw it back, I said, oh no. She throw it on me when she mad, she don't follow. She counting hundreds on the cash like a true boss. Don't you ask her for a hand, cause she take. She took a 40, threw it back, I said, oh Lord. She throw it on me when she mad, she don't follow. She counting hundreds on cash like a true boss. And don't you ask her for a hand, cause she do it. Oh baby, why you gotta be so savage? Why you gotta keep causing havoc? Is it cause you're real nasty? Got me spending money I don't have.
She'll take it deep and start the stars. Tell you only I'm just being honest. She'll take it deep and start the stars. Only I'm just being honest. She really ain't but being
your shadows in my room. Can't take back the love that I gave you. It's to the point where I love and I hate you, and I cannot change you, so I must replace you. Easier said than done. I thought you were the one listening to my heart instead of my head. Found another one, but I am the better one. I won't let you forget me. I still see your shadows in my room. Can't take back the love that I gave you. It's to the point where I love and I hate you, and I cannot change you, so I must replace you. Easier said than done. I thought you were the one listening to my heart instead of my head. You left me falling and landing inside my grave. I know that you want me dead. I take prescriptions to make me feel okay. I know it's all in my head. Shadows in my room, can't take back the love that I gave you. It's to the point where I love and I hate you, and I cannot change you, so I must replace you. Get me. I still see your shadows in my room. Can't take back the love that I gave you. It's to the point where I love and I hate you, and I cannot change you, so I must replace you. Oh, easier said than done. I thought you were the one listening to my heart instead of my head. You found another one, but I am the better one. I won't let you forget me.
never.
Mama was queen of the Mongol, Papa was king of the Congo. Deep down in the jungle, I start banging my first bongo. Every monkey like to be in my place instead of me, 'cause I'm the king of bongo, baby, I'm the king of bongo bong. I went to the big town where there is a lot of sound. From the jungle to the city, looking for a bigger crown. So I play my bongo for the people of big city, but they don't go crazy when I bang it on my boogie. I'm the king of the bongo, king of the bongo. Hit me when I come, baby. King of the bongo, king of the bongo. Nobody like to be in my place instead of me, 'cause nobody go crazy when I bang it on my boogie. I'm the king without a crown, bang it loose in a big town, but I'm a king of bongo, baby, I'm the king of bongo bong. King of the bongo, king of the bongo. Hit me when I come, baby. King of the bongo, king of the bongo. Hit me when I come. They say that I'm a clown, making too much dirty sound. They say there is no place for little monkey in this town. Nobody like to be in my place instead of me, 'cause nobody go crazy when I'm banging on my boogie. I'm the king of the bongo, king of the bongo. Hit me when I come, baby. King of the bongo, king of the bongo. Hit me when I come. Banging on my bongo, all that swing belongs to me. I'm so happy there's nobody in my place instead of me. I'm a king without a crown, hanging loose in a big town. I'm the king of bongo, baby, I'm the king of bongo bong. King of the bongo, king of the bongo. Hit me when I come, baby. King of the bongo, king of the bongo. Hit me when I come. Mama was queen of the Congo, Papa was king of the Congo. Deep down in the jungle, I start banging my first bongo. Every monkey like to be in my place instead of me, 'cause I'm the king of bongo, baby, I'm the king of bongo bong. Hit me when I come.
Fuck
Call it a dead cop. Rambo knife, show you what bloody is. You call it a dead cop, I call it a bloody pig. The biggest show in your career, like 100 kills. The AR-15 blew off like 100 wigs. Rounds blew off like a dead cop. That's a homicide. Blew off like 100 wigs. Show you what bloody is. You call it a dead cop. Rambo knife, show you what bloody is. You call it a dead cop, I call it a bloody pig. In your career like 100 kills. AR-15 blew off like 100 wigs. Rounds blew off like a dead cop. That's a homicide. Dead. Damn! Yeah? Fucking yeah? Are you fucking with me? You got a problem? Okay then. Ah, see we're not fucking around. Okay, we're not joking, are we? You're fucking dead. Fuck off!
You fucking psycho!
Fuck off!
Remember, I'm a bad person.
You are out of control! bucko, you know that? Some respect! You're fucking dead! Motherfucker! Fuck this! Bullshit! This is total bullshit! You're fucking dead! Fuck off! Bullshit!
My name is Kalashnikov. Kalashnikov. I am a professional.
From Russia with love, I fly to you, much wiser since my goodbye to you.
Kalashnikov. I am a professional.
It was called Desert Storm. The war began. Desert Storm. The war began. Desert Storm. The war began. Desert Storm. On January 17th, the war began. It was called Desert Storm.
Call it a dead cop. Rambo knife, show you what bloody is. You call it a dead cop, I call it a bloody pig. The biggest show in your career like 100 kills. The AR-15 blew off like 100 wind. Team rounds blew off like dead cop. That's a homicide. Blow off like 100 wind. To show you what bloody is. You call it a dead cop. Rainbow night, show you what bloody is. You call it a dead cop, I call it a bloody pig. Show in your career like 100 kills. The AR-15 blew off like 100 wind. Team rounds blew off like dead cop. That's a homicide. Like 100 wind. Team
Kalashnikov. Kalashnikov. I am a professional.
From Russia with love, I fly to you, much wiser since my goodbye to you.
Kalashnikov. I am a professional. I am a professional.
board. Hardcore. Hardcore.
I'm stuck in your space, just my luck. Push me away, you understand. There's nothing left to say. Pull me back, take my hand, call my name. You understand, I wanna say.
Yo, none of your business. I do what I want. This is my life. Don't act like a cunt. I'm surprised now. Look to me, you a fraud. You knew from the beginning what you brought. Hardcore. It's in my heart. It's in my soul. It's in my blood, not any control. If the bitch don't support the music, you gotta have the balls to choose it. It's in my heart. It's in my soul. It's in my heart. It's in my soul. If the bitch don't support the music, you gotta have the balls to choose it. Gotta have the balls to choose it. Hardcore. Gotta have the balls.
what you wanna do.
Un día yo voy a ser presidente de la República de Colombia. Plata o plomo, 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 plata o plomo. Plata o plomo.
¡Viva México, cabrones!
Everybody